Welcome to day 2 of the AI and AMR Symposium. Hopefully you had a great one and a very insightful day yesterday. So we are building up from what we discussed yesterday, and I hope and pray that today will be better and you'll get more insightful discussions, since you already have some background knowledge based on yesterday's discussions. So I'm delighted to have you once again. We can now begin the day. Our first talk, or I would call it a mini workshop, is going to come from Dr. Andrew Walakira and Akrut Eva, and they are going to try and show us how AlphaFold works. If you remember yesterday's first presentation, they were trying to tell us how AMR all starts from structure changes in the protein. Now they are going to tell us how do I actually get that protein. Thank you.
Good morning, our distinguished guests. Please. Yeah. So, all right. So we would like to just give you a little bit of, to show you a little bit of what AlphaFold is, what it can do. We do not expect you to leave this room as an expert of AlphaFold, but what we want to show you is that AlphaFold is real and can actually work. My name is Andrew Walakira, and I will be doing this presentation with my colleague, Eva Krut. Like I mentioned, so the idea of this session is that you get some idea about AlphaFold. Like some of you have been to these workshops, and we've gone through AlphaFold in greater detail. Due to the time constraint, I will not spend so much time on this slide. But what I need to touch on a few definitions or to help you understand. AlphaFold is a model. For the most part, AlphaFold 2 is deep neural network. AlphaFold 3 is a generative model, but to put everything together, I can say AI. So they are both AI models, and the idea is that they can predict 3D protein structures from a sequence of amino acids. And then AlphaFold 3 can actually also predict interactions, as my colleague will show you shortly. We talked about CASP yesterday, and I mentioned that CASP is a biannual competition, and the idea of CASP is that it helps validate these models, determine the accuracy and how well these models are actually functioning. It's a competition. Tomorrow, when you also develop a model, you could participate in this competition. And hence, AlphaFold 2 was actually validated in the CASP 14 competition. We talked about homologous structure. These are proteins with similar evolutionary origin. And then my colleague will mention something about the quality metrics. Somebody yesterday asked about how we interpret these structures in terms of how do we know that these structures are actually of good quality. So my colleague will talk about the quality metrics that we use. We have the one predicted local distance difference test. Basically, it looks at how well the model is predicting the geometry of the residues, the position and geometry of the residues. And then we have the predicted aligned error, which predicts the general or the global accuracy of the structure. So AlphaFold was developed by Google DeepMind, as we mentioned yesterday, and this is a company in London, works closely with Google Inc. So, like I've mentioned several times, the idea is to predict 3D protein structures, and here we exemplify some of the structures that were predicted by these models. But I want to interest you in the hemoglobin molecule. And because I want to use that opportunity to also talk about the limitations of AlphaFold. So we know hemoglobin is a protein Hemoglobin is a protein that transports oxygen and carbon dioxide in our body, in living body systems, in most of the living body systems. When you have a mutation on position 6 of the beta globin chain of hemoglobin, then if you have a mutation on that position with a change from glutamic acid to valine, then you have a disease called sickle cell disease. Now, what is interesting here is that glutamic acid is water-loving. It loves water. Valine hates water. So when you have that change, there's a change in structure, the stickiness of the surface of this protein, and hence you have this hemoglobin clamping together and forcing the cells to sickle, to acquire that sickle shape, hence the sickle cell disease. Now, AlphaFold, or these models, for as much as you may have those mutations, for as much as they are scientifically proven, AlphaFold may not show you those kinds of changes in the structures that you predict. If you get the hemoglobin sequence and then you change, because you can simply change on that position, you can simply change the amino acid. AlphaFold will not pick that significant change in structure. And the quality metrics may simply show you that the structure is fine. So this is one of the key limitations of AlphaFold that you need to be aware of. It is not sensitive to mutations. Like we mentioned yesterday, of course we are interested in how the proteins fold because that determines how they function. Also, here I'll mention that the AlphaFold models predict static structures. They do not predict dynamic systems of the protein. And that is also a limitation of AlphaFold. And also all the other models actually that are in this prediction space. You need to think about this, that when your proteins are when proteins are in a living system, they are constantly changing shape depending on the environment they're existing in, or depending on the function that needs to be accomplished at the time. So these models are unable to predict that dynamic state of things in a living biological system. So you also need to be aware of that. So these models predict static structures. So there are also parts of the protein that are called disordered regions. So these models may struggle with some of those, predicting some of those parts of the protein accurately. But you still, for that, it will show you that the quality of the prediction in that area, it will show you that it's not as good as the other parts where it can perform so well. So you should be able to see that, and my colleague will show you how to interpret those quality metrics. Yeah, like we mentioned yesterday, you can ably apply this technology to study drug-drug interactions, protein function. You can design novel proteins in silico and maybe produce them and try them in a wet lab system to validate their function. I also need to mention that these models were trained on evolutionary data, most of for AlphaFold 2. However, they were trained in such a way that they can predict even proteins that beyond what they were trained on. So for as much as they take in evolutionary data, they do not solely rely on evolutionary data to make their predictions, and that is a key strength of these models, and allows them to predict novel protein structures. So like any other model, the assumptions based on which these models were designed. The first assumption is that a protein structure is determined by its primary sequence, the sequence of amino acids, and indeed that is true to a large extent. Because once you have a protein, you have a sequence of amino acids. So it's from that sequence of amino acids that you'll be able to predict how the protein folds. I've talked about the evolutionary data, that these models take in evolutionary data, and here the assumption is that evolutionary conservation encodes structure information with the proteins having sequence similarity across species. So there are some proteins, for example, that are unique, that are in Drosophila, but they are very similar to proteins in the human being. That explains why you can have the Drosophila, a very small fly, being used as a model organism to study processes in humans. There's that kind of similarity across different species, and that is exploited when developing these models. So again, from the sequence of amino acids, you see as the protein folds, you may have, for example, the last amino acid turning out to be closer to the first amino acid when you do the folded structure. So the idea here is, or the assumption is that you can work out the geometry of these amino acids and predict how which particular amino acids interact with which other one, and to what extent do they interact, hence the ability to form the 3D structure. AlphaFold 2 and AlphaFold 3 were trained on existing PDB structures. Yes, of course, every model has to be trained on existing data, but what is interesting with these models is that they can even predict beyond the data on which they were trained. AlphaFold can predict accurate structures without the need for structure templates. Yes, you do not need to feed them with similar templates or related templates for them to give you a prediction. So all you need with these models is just feed it a sequence of amino acids and it will give you an output. Proteins fold at their lowest free energy, which may not always be the case in biology. So this is Anfinsen's theory, but the idea here is that you have this sequence of amino acid, you throw it in this model and it will give you a structure. However, you have to be aware that in a living system, the structure you have may not necessarily be what you've predicted because in a living system there are several other factors that come into play, things like pH, where the protein is localized. For example, if it's a protein that crosses the cell membrane, versus a protein that crosses the nuclear membrane. So you may have those differences. So AlphaFold may not be able to pick those very detailed differences in the biological system of the protein, how the protein is folding in a biological system. Then the other assumption is that static structure represents the function. So we are confident that the structures that we get from these models are informative enough for us to work with to at least generate a hypothesis or gain deep understanding about the protein that we are studying. And hence we can make some rational conclusions around the function of the protein and how to either inhibit it or inhibit its activity or promote its activity. With that, I will call my colleague to take us through a short demo. And again, I'll reiterate, the idea is for you to just have an idea about AlphaFold for those who have not interacted with it. Thank you very much.
Thank you, Andrew. So definitely I would kick off by stating that AlphaFold can be accessed through different ways, and those are the main ways. So you have a local installation where there's an access. You go to GitHub. Both AlphaFold 2 and AlphaFold 3 have repositories there. So you can download the code and then you'll be able to run it, and that will be the local installation. But you may not only use it on the computer, because most times you need high computational power, like GPUs. So chances are usually very high that you run it on a high performance computer, or you can run it on the Google web. All right. one of the first ways to access AlphaFold is the AlphaFold database that I think has been mentioned over and over again. Later on, I'll take you through that's the link to the AlphaFold database. And the key point here is that it provides over 200 million proteins, and these are for over 1 million organisms. Yeah, and of course the WHO pathogens of interest, which we know are part of the antimicrobial pathogens. Yes. Then the other is the Google Colab, which is the AlphaFold 2. This one, you can actually use it for commercial purposes because you have code that you can easily manipulate. Then the other is the AlphaFold 3. Now for that one, we currently don't have access to use it for commercial purposes, but you can use it for educational and also develop your proteins. Yes. So how do you search the AlphaFold database? Baby. Sorry. Yeah, it's not there. Okay, when you go in and search the AlphaFold database, when you click on it, all right. Sorry about that. So as you search the AlphaFold database, there's a search place there. So that is where you put in your organism, or you can search using a sequence, or you can search using the protein name. So you can use all those in the protein database. Then when you click search, you'll get results like that particular, like the result on my left, like to the left side. So there is the protein kinase domain containing protein. That is what they searched, and then you'll get results like that. So it would have the protein name, the gene, the source organism, the UniProt ID, the average PLDDT score, and also the sequence length. Then you could also, the beauty about it is it will give you other multiple sequence alignments. Also, you can carry out a blast to confirm the protein and look at which proteins are similar to it. Yes. Then, so this one is, I demonstrated using a protein called a lysP, which is a lysine-specific permease protein. So for it, I carried out the database search right there. I did a lysP search. So, and this is what you get. So on top of the previous results, you get what they call a summary and model confidence of those structures that are already in the database. So there you'll have the domains, you'll have annotations, you'll have everything you need to know about the proteins, and also where else the protein is hosted. Like this one will show you that it's hosted in UniProt. It also shows you the organism. So you'll be able to click on it, and when you go into the UniProt database, you should be able to find out much about this particular protein and the microorganism, who submitted it, what is the biological function of this protein. Like there's a lot of information just if you use it to access the AlphaFold database. So in the AlphaFold database, because this structure is already predicted and the information is readily available, you're going to find that it has the prediction scores, that the prediction matrices that my colleague mentioned. So right there is a predicted aligned error, one of the matrices that you use for assessing the structure of the protein. And it's always good that you don't use only the predicted aligned error, but you have to use it in combination with the PLDDT score, because it will show you which region that the AlphaFold model predicted very well. So if you're looking at the PLDDT score, so right here on this, sorry, I can't use a pointer. Okay, sorry. So that dark blue region is that structure predicted that protein very well, and then the lighter blue is fairly predicted, and then the orange is poorly predicted the protein. But as you can see on the on the right this side, that from the PLDDT distribution, you have 86.88, so it's actually quite high. So that means you're very confident that this protein structure, this protein, that is the correct structure, because what it does, it compares it to a structure that is like experimentally validated. So you can use this particular structure with confidence if you have a score of 86.88, and then right there it shows you how much of the residues have that score. So you have a 56.4 of those residues being predicted very highly. So you can use this particular protein with confidence. So the next step is the other way to access AlphaFold. So we use the collab fold. So the different steps of the collab fold. So we shall open the collab notebook, and then we'll input data, as my colleague mentioned, because it uses the primary sequence of amino acids. So that is the input that we shall put in. And then you go ahead and install dependencies that for the model, that the model is going to use to predict the structure. And then the MSA, the multiple sequence alignment options are also there, the advanced settings. Then you run the prediction, display the 3D structure, the plot. And the beauty about this, you're able to download the final predicted structure, and then you can manipulate it using other visualization tools like PyMo and Chimera X and JMO. Yes. So for this, unfortunately, we had a problem with connecting to the internet, so I might not be able to fully demonstrate it, but right here is how these are the various steps that you take. So remember that in the AlphaFold database, we picked out the LysP protein. So from it, you're able to download the sequence. So you can copy the sequence, and here, or a protein of your choice, right? You could have, maybe you're designing a vaccine, so you get different peptides, then you link them together, and then you have a primary sequence of amino acids. So you can use that particular place where the query sequences is where now you'll feed in, your sequence from the multi-epitope vaccine. So these are the various steps. So the collab fold looks like this. It has been updated. They keep updating it. So as you can see, started from version 1.4, and currently we're at version 1.6. So if you want to use the previous notebook, you can always click on it, and then you'll be able to access that particular notebook. So the first part about it is you input the protein sequences. Then you can run, like on the topmost part, there is a runtime, command, code, text, run all. You can run all, but then sometimes you want to interact with your prediction, right? So it's better you run each particular cell where there's that button, this button here. You can click run, and then it should be able to run. So so the very first option is to input your protein sequence, and then here you can change the job name to the name of your choice. This one I left it as test, but if maybe you're developing a vaccine, you can put your vaccine name. I prefer to leave it in default, but you can, this num relax has different, like it has different numbers, so you can keep changing it. Like you just keep trying on manipulating your protein, maybe to get better results. Yes. So the template mode is none. It's always good practice to first run with the default parameters, and then you can be able to change. So when you run, after it has run successfully, it will bring the job name. It will also tell you what sequence you inputted, and also the length of that particular sequence. And then you'll now go in and install dependencies because you're using collab fold. It has code for collab fold. So that is what it will use, and then it will also assign what the CPUs that it's going to use, and also it will tell you the total time that particular cell has run. So here in the next step is the MSA. So here you can custom like your MSA. Maybe the predicted structure is not what you want, and then you've carried out a blast. So you're going to carry out a multiple sequence alignment. So here, if you want to maybe improve your prediction, you can feed it. There's a drop that says custom, so you can put in the custom option and then incorporate in your custom made MSA. Yes. Then the next part is the advanced settings. Here I prefer to use it in auto, but there's an option where you're predicting more than one protein. So it's like multiple proteins. So there's an option here that is the AlphaFold Multima. So you can click on AlphaFold Multima and then separate those sequences with a full colon. Then when you run, it's able to give you a predicted structure of the two proteins that are combined. Then these are the relax maximum iteration, so it keeps iterating. So depending on how long you want your protein to, because every time it iterates, it refines the model, it refines the protein structure. The default is 200, but you can increase depending, because sometimes the more you increase or decrease, the longer it's going to take to carry out the prediction. But by the time they put it at 200, I believe that they had tested it and worked really fine. So the pairing strategy is greedy, but you can also keep checking it. Then the next option is to run the prediction. So when you run the prediction, here it will show you of course it goes through the databases, takes out the similar proteins. Remember, Andrew mentioned the evolutionary relationship of these proteins. So it will look at similar sequences, then carry out multiple sequence alignments on them all, and then they will map it to the original sequence. And then it will show you that the similarity and identity across those different species. And here, because we set it to run 3 cycles in the advanced settings, so those are the number of times that it will carry out iterations. But oftentimes it's up to 5, but sometimes after 3 iterations, whether it runs again, the structure won't change, so it would stop at that level. Like there's no particular change in the structure. So, so from this, it will, of course, that you can color by nucleotide, you can color by the PLDDT, which most of us should actually use because it will tell you the quality of the structure. So, right here, these are just results. All of them are from the prediction, so it will just keep showing you, like, this is the first iteration, that is how the structure was, and then it refined it further, and then this is the final refinement. If it ran 5 times, it will give you all those different outputs. Yes. So those are the ones. Then afterwards, we need to display the 3D the 3D structure of the protein. So sometimes there are challenges with the AlphaFold code. So you might get some errors, and so you have to debug them. The beauty about AlphaFold is now that it has Gemini installed in it. So when you get an error, you can run. Okay. you can run the Gemini, and it's able to change the code. It will tell you what the error is and then also change the code. So I carried out some debugging, and then I was able to visualize my particular protein. Yes, so those are the results of that. So that is AlphaFold 2 for you. So that means that I've gone through all this. Yeah, so then I used the very protein because I had the sequence, and then I put it into the AlphaFold 3 server, so and predicted its structure. So it had a slightly improved PLDDT. In AlphaFold 2, it was at the PTM scores. The other side, it was at 0.83, and then in this particular one, it improved to 0.88. So there was slight improvement, but you can use both structures because they're above 80, so they could be used. So what you need to know is nothing in biology makes sense except in the light of evolution, and that is what Thaddeus mentioned. But in the AlphaFold context, nothing in AlphaFold prediction makes sense except in the light of confidence matrices. So at least from this talk, you should come up with this. You should take home this particular point. So since these ones have already been mentioned, I'm not going to talk much, but that is, yes. So that is how the PLDDT matrices are. So after your structure, you're able to go through the structure and see which particular regions have low confidence, which ones have high confidence, and you're able to see which amino acids actually in those particular regions. And then for the aligned predicted error rate, you're still you can maneuver through and see which amino acids are in those positions, especially the dark green regions. So as I mentioned, it's important to use the two together, the predicted aligned error and also the PLDDT. So for the AlphaFold 3, this one I already mentioned, so you can access it using AlphaFold 3 or the GitHub repo. And maybe what does AlphaFold 3 predict? Predicts proteins. Of course, because now they've advanced it to, the other one was only focusing on proteins, but now here they've stretched it further. You have RNA, you have DNA, you have small molecules, you have ions, you have modified residues, but it doesn't add the water and the hydrogen molecules to the structures. So those are just some of the examples. So when you go to the AlphaFold 3 server, there are the example structures, or the example structures. So right here is on one of them. Because it predicts interactions. You can predict a protein, an RNA, and an ion. You can predict a protein, a glycan. You can predict the methylation. You can add an ion. Yes. So what you do, I don't know if I put it here. No, I think I did. So on the AlphaFold 3, there is, I'll check and see if it's the other side. So with the AlphaFold 3 server, there is a space where you put in your protein sequence, and then you just keep adding. On your left side, you can add what the compound is. If it's a protein sequence, you select protein. If it's an RNA, you click RNA on the drop down. If it's DNA, if it's an ion, so you can do all that. Yes, and maybe I would leave you with this. So if you want to study more about AlphaFold, you can just scan through there. It will take you through to their course. It just takes you about 3 hours, and I believe by the time you finish those 3 hours, you should be very conversant with what AlphaFold is, how does it predict structures, what are the limitations, how do they cite, what have people used it for, what structures do you use? Yes. So maybe I would just end with this. So after you have your structures, then what, right? So you need to visualize them. So there are manipulation or visualization tools like PyMo or Chimera X. Those are the ones that I mainly use, but also highly recommended by very many people. If you read a lot of publications, you find that those are the ones that are commonly used. So, so you can go to the PyMo website. It's a Schrödinger. It's hosted by Schrödinger. So you will launch it, but it requires a license. So if you're a student, you can use the educational option. If you're not a student, you'll download it. But sometimes it will always keep flagging. Like if you didn't download the license. But so for it, what you do is if you're using it for the first time, you skip the activation, then you create a folder that you're going to use to put in what you're going to put in your protein work. Yeah? Then it will automatically reflect on the PyMo on the PyMo itself, on the PyMo terminal. So this is just an example. So you enter PyMo, and then in the PyMo on the left side, there is the very first option is file. So what you do in there, yes. So what you do in there is you can fetch the protein from the protein database, from the protein data bank, from UniProt, or you can select the protein that you downloaded. So for it, for the fetch is when now you can go to the online databases to fetch your protein with the unique ID. And then for open, you just open the protein that is right there. Yes. So I think that is all. And then for Chimera, you can visualize using that. You can reach out for if you have questions or more training, we'll be willing to help with my colleague Andrew. Thank you.
Thank you so much, Akurut, for that wonderful presentation. Hopefully we have learned a thing or two about AlphaFold, and then those who already knew about it, hopefully you have grounded the knowledge. Yeah? Then we are getting one question from the audience, and then one question from the audience. He's asking whether they can have access to Google Colab.
Yes, it's you just need a Google account, which is mainly Gmail, and then you can access it.
I have a question. I will comment. Good morning, everyone.
Good morning.
Aloluwasheun is my name. Concerning the AlphaFold system, you said something that you can be upgraded. So my question is concerning the user-friendliness of this system, because I'm coming from computer science aspects now. The user-friendly of it, because when you were doing your presentation, for the first time user of the system, it might look somehow. So please put into consideration the user-friendliness of the system. Thank you.
All right. Thank you, but I could just talk about that slightly. So it's actually very user-friendly. So for the AlphaFold 3, it's usually just a click. All you just need to do is input in your protein sequence, and then the model does the rest. And you have to know how to, like, you have to know how to explain the structures that you get at the end of the day, like the quality of the protein. But that is why I pointed you to, they have a 3-hour course, a short course. By the time you finish that course, you can be able to manipulate like most of it. But AlphaFold 3 is very easy to use compared to AlphaFold 2, and maybe from the computational background, it uses Python, like Python programming. So you don't need to know the code. But as a computer person, you may want to know what is the code doing, so you're able to see what the code is, and you should be able to manipulate that. So it's just that all you need is you just click that run, like you just keep clicking that run button, and you'll generate your structures at the end of the day. Yeah, it's clear cut actually. Thank you. Thank you, everyone.
Welcome back from the previous session. As I said earlier, hopefully we learned a thing or two about AlphaFold. Remember, they've told us nothing makes sense in the face of AlphaFold without the metrics. Hopefully we have understood the different metrics that AlphaFold uses. That is the PAE, the PLDDT, and so on and so forth. You have a question? I'm seeing someone's hand is up. I'm going to come and I talk to you after here. So our next session comes in from Atwine Mugume, who is a health data scientist and a machine learning engineer. His work focuses on applying artificial intelligence and natural language processing to improve clinical decision support and health informatics in low resource settings. He also contributes to the OHDSI Uganda chapter and teaches machine learning and data science. So a round of applause for Mr. Twin.
Good morning, everybody. Can you hear me?
We can hear you.
Can you hear me clear? Okay, thank you. All right, so thank you everybody for making the time. I'm going to take you through what we've been doing at the S, but also just give you an overview of what the current status is with AI. I know a lot of us are interested in it, and we have been talking about it since yesterday. So my focus right now is just to show you a couple of things that would be able to work in low middle income countries, some of the things that we have discovered over the years with the projects that we have done at the S. Hence my title, What Actually Works. Okay, so when we talk about AI, I know a couple of ideas come to mind, and I just chose a few of them, not exhaustively. So we would normally talk about predictive analytics, your predictions, the algorithms that you see, the publications that you're making, where you give data to an algorithm and it's able to learn and predict for you on unseen data or out of sample data. Then we'd have of course, deep learning, natural language processing, which is a very critical area right now. How do we communicate to machines? How do we do translations? How do we get the machines to read our documents, and then with interact chatbots and all kinds of things. Then a not so much talked about thing is optimization. How do we get AI to optimize our power grids, our railway systems, and all these kinds of things. And all this is very, very interesting stuff that is happening. And of course, we talk about vision. How do we give the machine eyes to be able to perceive the environment? How do we train self-running cars and all these kinds of things? So this constitutes a lot of what is happening right now. Not conclusively, but most of the stuff that I'm talking about right now, I'm sure you've interacted with or seen. So I just want to I want to just share some thoughts in regards to a couple of things. So, and I want you to start here. What exactly does it take to get some of these systems up and running? What makes AI work? Right? We talk about it and we talk about models, but what actually happens in the back end? So obviously we know about data. Right now we are able to collect data massively. When you talk about big data, we have the capacity to collect petabytes of data in just a short while. So we have all types of data structures and sensors and data lakes. So AI would not be really functional right now without data, because all the insights and all the things that we are building upon are related to the kind of data that we have. So once we have our data, we are managing it correctly, we are processing it and labeling it correctly, then we would have the model development. So that talks about algorithms, architectures, model training, evaluation metrics, etc. And then most of the researchers I've interacted with normally stop at the development part, but we also have the deployment where we talk about machine learning operations, model observability, monitoring, ethics and governance. So this is generally the framework or the ecosystem of what it takes to get models up and running. Oh, sorry, forgot to put on my camera. All right. So I then wanted to give you a picture of, we have these things, these nice things that we're seeing. We are interacting with ChatGPT, you're interacting with Claude, you're interacting with all sorts of beautiful systems. But if we look at the back end now, not just the front end, the nice stuff that click and run, at the back end, what exactly does it take to get this kind of system up and running? So this is just an overview. I'm not trying to really, get very technical, but I'm just showing you that at the back end, when you type ChatGPT in your web browser and you ask a question, there is a whole mass of infrastructure that comes into play. And this is what it would probably look like the back end. You have nodes at the bottom, starting from the lower layer. You have clusters, you have nodes, you have GPUs, TPUs that are calculating huge masses of data. And then you need a way to distribute this information because you're connecting remotely. And then if you're connecting remotely, you need to manage latencies, bandwidth, schedule the right jobs, and then do all sorts of automation. So it's a layer of things that are happening. And why is this important? It's important because when you begin to consistently feed off what, ChatGPT and all these things, what's happening there, sometimes you forget that you might have to see what's happening in the background if you're going to be able to replicate such systems locally. And that's important because we quickly run into problems because of costs. For example, if you want to put this kind of thing up on your side and you have no idea, you don't realize the amount of money that goes into keeping such systems up and running. We have had some experiences at the S putting up the HPC infrastructure. It has been a work in progress from day one. So this is just another picture to show you I think the ballpark figure that you should see on the top is if we want really to set up something as good as some of these big tech giants, it would be around yearly $650,000 to 1.4 million USD to get that thing up and running and consistently. Of course, there are several other factors. So that the breakdown, the details that you're seeing is the breakdown that it would take to get this kind of thing up and running. So there's several layers. So it's not so easy or so straightforward. It's not plug and play, as my director likes to say. It's not plug and play. There's a lot that goes into it. Okay, so there are costs, one-time costs, there are infrastructure costs, there are distribution, storage, data models, region transfers. All these things cost money. Okay, so obviously the picture I'm trying to build is it might be a little bit hard for a simple organization to get some of these things up and running. So the idea is when we are not able to do that, then we are pushed into certain corners. For example, if you're not able to build or train your own algorithms or fine-tune them, you would then be forced to use some of the algorithms that have already been pre-trained. And that could expose you to algorithmic biases and misdiagnosis, because in the health field, these kinds of things are very important. Even in other fields, having context-specific models is very, very important. So that's one of the issues. Then you have, of course, data sovereignty. Where is the data kept? Who has access to it? This is a very big question, and it's something that causes a lot of problems. So if you don't want your data to be sent somewhere you're not sure, then you might have to consider building or setting up some of these things locally on your infrastructure, right? So, and because of this kind of setup where you don't have a lot, then you have stifled innovation and development. You can't do as much, right? You can't explore as much. You can't, for example, you can't deploy a model of billions of parameters at full precision, maybe like 16-bit precision or 32-bit precision. So as a result, you end up being dependent on global tech giants, and sometimes you have to make some tough decisions between, do you budget for a full AI team or do you budget for something else? So there's something that you want. You want a fully functional system, you want hardware, you want all sorts of things. But the reality is you have power cuts, you have connectivity issues, you have hardware issues, and you have low bandwidth and all these kinds of things. So at the ACE, what we've been trying to do over time is to try and figure out how do we then replicate what we are seeing online, and then make it possible for us to work in low resource countries, or if we can just say in small organizations with not so much budgets, with not so much infrastructure. So the question is, how do we get from where we are to where we want to be, where we don't have to hustle with data policies and have costs spiraling and the questions of continuity when the project, maybe some grant projects reach an end. How do we ensure continuity? Because you have to pay for API calls and all sorts of things. So how do you get scalable infrastructure? So how do we get from the left to the right and not just talk about it? Okay, so I'm just going to go through a couple of things that we have tried and seen to work over time. Okay, and I believe some of you can take some notes from it and be able to try in your own environments. Okay, so one of the first things that we saw that was important is the capacity to embrace open source. So earlier on, as we are working through these processes, as we are learning day to day, we found we had problems. Some of the softwares that we wanted to work with were not fully functional for the kind of use cases that we had. So we needed customization flexibility. And it really most of the projects we had to take time out to look at what is the best direction to go. But most of the times off the shelf softwares we'd find we have issues like vendor lock-ins. This is where you find you've hit a certain point and you're not able to access some of the resources that you would need because the vendor needs a couple of thousands of dollars or euros for you to pay. So that becomes a problem. So with open source, you have capacity to do customization, you avoid vendor lock-ins, and well-built open source software, you have a huge community with which you can collaborate with. And the barrier for entry is really low, so you don't have to really struggle to get things up and running really quickly. You can just download something off of GitHub. There's a way to figure out how that works, but there are some good engineering communities that have set up some amazing open source tools that can really help people to get up and running. So this in turn reduces your costs. If you have infrastructure, you don't have to spend so much if you're running open source tools. And some of these open source tools that I will be looking at are things like Olama and Onyx and several others that have helped us do a couple of things that are quite amazing right now at the moment. So the question is then, how do you know when you should go open source versus picking off the shelf software? So there's a criteria you can use, and of course you're welcome to try, test, and evaluate and see what works for you. So, but some of the factors that you can consider are things like how much volume are you working with? If it's really, really like high volume, then you might want to go open source because some of these expenses, they increase with the capacity of data that you're working with. Then the really, really big one is the sovereignty, the sensitivity, data policy, and the laws. If your data can't leave the country, if your data can't leave your location, your specific intranet network, then you might have to have on-premise kind of infrastructure to work with. You can also look at the latency. What's the response speeds of the kind of use cases that you're working with? Do you want faster responses? Do you want, is a 500 millisecond response okay? So these are the kinds of things that you can look at to be able to tell, and this also can guide the decisions that you're making as you're building some of the projects. Do you have the expertise that you need for you to be able to set up? It's not only a data scientist that you need a full team, you need developers, you need engineers, you need MLOps people, you need, of course, the scientists have to be in play. So if you don't really have a good team, then you might be able to just choose the off the shelf. And of course, if you're talking about expenses, if you need predictable expenses where things don't just pop up, because there's a way these off the shelf models or these people are hosting these things, sometimes you get surprises on the quotas. You have quotas, you have limitations, and those types of things that it's hard for you to predict your cost. So these are kinds of the things that you would like to look at if you're going to choose, and some of the things that we look at when we are choosing whether do we go open source or whether do we just pick off the shelf. But most times we find ourselves dealing with open source because the biggest issue is the data issue. Most of the data, especially health data, it has some special considerations that you have to put in place before you expose it to a public infrastructure. Even when they promise that it's safe and whatever, we sometimes are not really, really sure. So there are some questions that you would need to ask yourself, some questions that have to be answered if you're going to be able to set up some of these systems, like local inference. If you're going to set up these systems locally, what do you need? Is it local inference? And how is it going to be possible for you to run this locally? Are there softwares that can help you run this locally? So for us, for local inference, that is building systems that can be run locally on our infrastructure, we use So I'm going to be showing you just a couple of things that we have been finding useful. So we have this open source tool called Olama. So Olama is a pre-built API framework that you can run on your local infrastructure. The idea is once you install it, you can install it locally on your machine, or you can install it on your servers. If you have CPU servers and you want to run a couple of models and try out a few things for your research or something, you can use Olama. Olama is open source, and they have done most of the heavy lifting for you. So if you have maybe a GPU on your computer and you install it, it will automatically detect. If you didn't have Olama, then you'd have to write the code for the APIs and all these things, which I know some of us don't have the capacity to. So with just this tool, we have been able to download a couple of models, do some tests, back-end, front-end tests, apply some paradigms of machine learning and deep learning, like RAG architectures. This has made it easy for us to evaluate, learn, grow, appreciate the kind of engineering and science that we would need to go through if we are going to function effectively and build integratable systems. So Olama really helps you. It has many benefits. Of course, it can run on your CPU. If you have big models, you can quantize them and they would run on Olama. So it would help you do things like text generation, summarization, translation, all these things that you see ChatGPT doing. There's a lot of engineering that happens at the back, like summarization and running context-specific. If you have maybe like data that you need your model to look at and not do hallucinations, you need to write like RAG architectures. So several use cases, all the things you can do on ChatGPT, you can actually work with it locally using Olama. So you can test a couple of things, a couple of architectures, a couple of models, and that would help you really appreciate the kind of direction we would need to go if we are going to pull off these types of systems in Africa. So the next question would be scalability. So you have Olama on your machine, you have 1,000 users, and would you be able to support 1,000 users as easily as you'd support 10? Or can you scale or add more infrastructure without having to rebuild the system? So that is important. And for that, we have been able to find lightweight Kubernetes infrastructure that we've been working with for a while right now. So what this does, it helps when we have increased usage, when more people want to connect to our networks, then it automatically increases. And then when they log off, it automatically decreases. So this one is really lightweight and it's very, very easy to set up. So normally if you're to set up like a normal Kubernetes infrastructure, what you're looking at, if this is giving you a headache, then exactly this is what you would have to do technically to be able to set up a fully fledged infrastructure with Kubernetes. So this lightweight version, K3S, is easy to install. You can actually run one command and it would install within like 30 seconds and be able to support most small infrastructure use cases that you would have in small organizations. I know we are not really, some of us have not reached the capacity where you need like fully fledged, because that would mean hiring Kubernetes experts to be able to take care of this kind of infrastructure.
Excuse me, Atwine.
Yes.
Kind reminder, I only left with 3 minutes.
Okay, thank you. All right, so then we talk about productionizing. And when we talk about productionizing, we are talking about, can we turn the code that you have in your VS Code, how do you quickly productionize it and get it into working models and For that, we've been using BentoML, which is something also that you can look at. Of course, I'm going to share the slides, and then you'll be able to look at some of these things personally. And then when we talk about information retrieval, can we connect to our AI to all our existing data sources? Can we guarantee that we are getting the right context-specific advice or information? So for that, we've been using a platform called Onyx. It's another open source platform with a huge network of people who are supporting it. So with this, you're able to set up so much RAG systems and all these kinds of things. So it would support you quite quickly and in a handy way. So if you need to get up and running with the front end, that would be the best thing for you. And it can connect directly to external off-the-shelf large language model providers and API providers, and also Olama if you have the technicality to do so. So at the end of it, when we do a quick comparison, you find that there is actually a potential to have these things up and running at a fraction of the cost that it would take if you are going to set up a fully fledged infrastructure yourself. So this summarizes kind of the costs. On the left, you'd have the enterprise system, and then on the east, you have a lean stack that you would get up and running. And then, of course, the last thing that I'll talk about is the collaboration capacity. If you really want to get some of these things up and running, you have to work together with the rest of the community that is doing AI. So you find you have the expertise, but you don't have, the infrastructure. So there's need for us to work together if you're going to be able to pull off some of these things and be competitive in the market. So yeah, thank you so much. That's the end of my presentation.
Thank you, Atwine, for such an insightful presentation. You're going to have 2 or 3 questions from the audience.
All right.
Thank you very much. I forgot the name. So just a quick one. Yeah, I think it's quite difficult to pronounce, but thanks. But then my question goes like, you mentioned with respect to Onyx, and I was quite curious with what Onyx was offering in terms of it being large, it's providing UI interfaces for you to embed your models or stuff. So I quickly glanced, and I know they are quite tools like Chainlit and Streamlit that offers also more, potential, beneficial to also users who want to embed such models from either, Olama or Hugging Face. What does I think Onyx offers more than these two? Because I think a lot of users and us are quite, formidable and compatible using Streamlit and Chainlit as main chat UI to embedding such UI models. Thank you.
Okay.
One more question.
Yeah, thank you, Atwine, for the amazing presentation. A founder of a startup that is embedding AI to solve antimicrobial resistance. And my question is, what would you advise us? Would you advise us to go open source or get an IP? Thank you.
Okay. So I'll deal with the first question. So it depends. Streamlit is, we use Streamlit a lot for what we call MVPs, minimal viable product. If we have a use case that we want to test and see if actually the idea works, we use Streamlit for that. But if we are talking about building something. For example, if you want to use RAG with Streamlit, you'd have to probably write the code for that in the background, how the embeddings are going to be functioning, which database you're going to be using. Is it Pinecone? Is it what? And how is it retrieving the data? Does it use cosine similarity vector, whatever, all these kinds of things. I would need to think of that if I'm running with Streamlit. If I'm trying to build something where I don't have to think about all those things, but I can just review what has already been made, then I go with Onyx, right? So I set up Onyx. In the back end, the engineers have already set up the Pinecone databases and all these things and all the connectors, because with Onyx, I can connect to multiple interfaces. I can connect to multiple, they call them connectors. When I can connect to Google, I can connect to news providers. They have a couple of APIs that are already running that you just click and it's plug and play. So it saves you a lot of time in terms of writing code and setting things up. If I was using Streamlit, I would have to write those things myself. Okay, so when I have a short time frame or when I have to set up something quickly and productionize it without having to have like a huge team, I would go for the Onyx front end, because most of the things have already been done. And it has so much support online. So that's what I would say. That's the experience that we have had. And for a startup, really, it depends. You know, the criteria I showed you, you'd have to sit and look through the criteria and see what numbers do you have, what speeds are you expecting, what capacity do you have? Do you have developers? Do you have a team that would help you to get up and running? If you don't have that kind of team, then maybe you want to go for the open source. For the people who are selling APIs, the kind of data you're dealing with. If you're dealing with data that is okay, like maybe you have, I don't know, some data that is not so sensitive, that doesn't identify people, you may as well say, okay, let me just go with this direction of getting ChatGPT or some of these guys to work with you. So it really, really depends. It's a conversation that you'd have to have internally, or maybe with someone more technical to help you figure that out. So I can't give you a direct answer because I don't know all the variables that are in play. But yeah, it depends. Thank you. Over to you, Rachel.
Thank you so much, Atwine, for this wonderful presentation. A round of applause to Mr. Atwine. Thank you. You can, it's okay if you go off the call. Yes. Okay, we are moving into break. It's going to be a very short break, but the break also involves viewing the posters. So we request those with posters to go to their posters. And then I kindly request you that by 10:50 we are back into the room. Thank you. Have a nice break.
For those who haven't had a chance to present your posters, you'll be able to do that at lunchtime, so don't worry. So our next speaker is Professor Allison, and I'd like to invite Dr. Daudi Jingo to invite her. Thank you.
Okay, I hope you all had a good break and you're set for the keynote address. Usually for conferences and symposia like this, the keynote is the highlight of the conference. So I hope you're all ready for that. And we are privileged to have none other than Professor Alison Holmes to give this keynote today. Alison is a physician scientist in infectious diseases and the inaugural director of the Fleming Initiative, which is a leading global effort to tackle antimicrobial resistance through integrated research, policy, and public engagement. She's a professor of infectious diseases at the Imperial College of London and has made major contributions to improving infection prevention and antimicrobial stewardship. She co-founded the Antimicrobial Optimization Network, CAMUNET, which is an international research collaboration supported by the Wellcome Trust, focused on improving antimicrobial use and addressing MR across multiple countries. There's a lot of people in the room who have actually worked with the CAMUNET network over the last several years. And as is, we have benefited immensely from that. Alison previously served as the president of the International Society for Infectious Diseases and contributes to WHO expert groups and global advisory boards. In 2025, she became a co-founder of the World Economic Forum's Global Future Council on AMR, where she continues to influence global health policy. Alison has also been a major supporter of the S, has introduced us and connected us to a lot of important international fora and bodies, and so we continue to benefit from her. And by the way, Alison, I'm giving this away, Alison also has important connections to Africa. I think she partly grew up in Africa, so she understands this place quite well. So Alison, we're really looking forward to your presentation, and off you go.
Fantastic. Well, thank you so much, Daudi. Can I check? Ooh, that's terrible echo. Can I check you can hear me okay, Daudi?
Yes, Alison, we can hear you loud and clear.
Okay, fantastic. Well, what a build-up. Thank you so much, Daudi, and thank you all for inviting me to participate in this fantastic program. I'm really sorry I am not there. I was looking forward to being there in person, so I am very sorry that I'm doing this from a computer in London. So as Daudi mentioned, I'm now the director of the Fleming Initiative, and I'll just tell you a little bit about that, and then I'll talk a little bit more about how we're using artificial intelligence in our work. And clearly, I know very little. My background's in infectious diseases, but I am blessed by being surrounded by the most extraordinary colleagues and experts. So the Fleming Initiative, which is not the Fleming Fund, is a organization based in London, because that's where Fleming discovered penicillin, that we really are looking at collaborative approaches to address the global challenge of antimicrobial resistance. We are particularly interested in science and innovation and the opportunities with artificial intelligence and bioinformatics. We're working with world leaders, and it's not just about research, it's about how can we also address all the challenges related to legislation, policy and regulation, and also how can we absolutely make sure that we take the public on board with us, society on board with us, and policymakers on board with us. So that last picture is a poster. It was an incredible takeover of Times Square during the UN General Assembly to raise the profile of what's going on with antimicrobial resistance. So opportunities to raise awareness and engagement are absolutely critical, and keeping society involved is absolutely part of the work we do. So the next thing is that we arrange our work around kind of three key pillars: science and innovation, public engagement and behavior change, and informed policy. And as I said, the reason it's in Paddington in London is because this is the site of that tiny, dirty little laboratory where Alexander Fleming first discovered penicillin. I mean, the most extraordinary discovery, completely has changed healthcare, completely has changed humanity. One of the greatest resources that man has developed for extending the lifespan of individuals across the globe. And we have really squandered it, and we need to do much more about how we can preserve antimicrobials for our generation and the next. So he discovered this in 1945 and was awarded the Nobel Prize in 1928. And our mission is to keep antibiotics going for at least the next 100 years. So this is St. Mary's, and this is the planned building for a Fleming Center to celebrate his work, honor it, but also to bring science, policymakers, and society together. So he got his Nobel Prize for the work he did in 1945. And in 2025, I was invited to Sweden to the Nobel Prize dialogues to celebrate and discuss the issue of antimicrobial resistance. And I'm putting up this photo for you guys because I've seen on the program you're talking about AlphaFolds and Google DeepMind, and I just want to point out that what a pinnacle of my career that I was there on a platform with Paul Nurse talking about the importance of artificial intelligence and scientific discovery. So I thought that was pretty amazing to be able to do that all through the work of Alexander Fleming. But sticking in Sweden, I just wanted to say that as well as going to the Nobel Prize dialogues in Sweden, in Gothenburg and Stockholm, I was delighted last week to meet another hero in Uppsala in Sweden. So it's really wonderful to have Dowdy Jingo at this meeting between the Wallenberg Foundation, the Scientific Life Laboratories, the Fleming Initiative, and the UK Science and Technology Office. And this is all, and also one of our Google DeepMind fellows. So it was really wonderful to have the participation of Ugandan leadership at this particular meeting in Sweden. And as Dowdy says, all of this is also based on a background of fantastic collaboration through Camonet with our colleagues in Uganda. And as Dowdy says, many of them are in the room now, and I'm indebted to the fantastic collaborations there. So as I said, we are really committed to doing everything we can to harness artificial intelligence to address this major global challenge of antimicrobial resistance. And this is a paper that came out from one of the meetings at the UN General Assembly about how critical it is that we use this expertise and this growing body of experience and leverage it to address one of the world's one of the largest health crises of the world. And it really calls upon us to take action across a range of areas. And this is Lord Aradasi, who is the executive chair of the Fleming Initiative, in which I am the director. So moving on, I just want to give, as a first example, this incredible piece of science, absolutely amazing, led by colleagues at Imperial, Jose Penades and Tiago da Costa. Incredible work on uncovering what was happening in the formation of phages in terms of moving around pieces of DNA. Really highly elegant science, many years of work to design these experiments, to understand how they transfer packages of DNA and antimicrobial resistance genes around. Incredible, beautiful, detailed research. But what I want to draw your attention to is the paper that's quoted at the bottom, which is AI mirrors experimental science to uncover a novel mechanism of gene transfer, crucial to bacterial evolution. And so just like the kind of concept of driverless cars, we now have the concept of driverless laboratories where AI can unlock all the experiments and predict the experiments that are needed to find out what exactly was going on at the molecular level with phages. So this is a project with Google DeepMind, with AI co-scientists predicting the complex gene transfer that they were looking at. And the artificial intelligence generated hypotheses completely then opened up new research directions. And it took years and years for Penades and Tiago to develop this incredible science. But meanwhile, the AI co-scientists planned the experiments that were needed to test the hypothesis within 2 days. They were dumbfounded by it and questioned whether or not that they had been accessing a variety of meetings, etc. So I just want to flag to you, not only are we interested in artificial intelligence, in drug discovery and in epi, etc., but also the applications of artificial intelligence in the laboratory. And this was quite amazing work published in Cell, and it was one of the most highly cited papers last year. Absolutely fascinating how this could be done. So next, I'm going to shift from how we can use it in the laboratory and that amazing breakthrough about how it can actually take years and years and years of work, experiments, hypothesis generation to design some incredible groundbreaking science at the same time as colleagues were doing it. So I want to talk a little bit now about what we're doing in terms of how we're using AI for antimicrobial resistance surveillance. And that goes from right at the beginning, how we generate the data that we can then use in artificial intelligence, how we can use it to process large amounts of data, from using language models and applying to clinical coding, how we can integrate data across sectors, how we can store it, and then how we can analyze it, how can we present it in the best way, how can we use the best of data visualization and real-time feedback to support interventions and monitoring, and also then how can we mobilize knowledge, and how can we use AI for policy, and also making sure we address governance and ethics at the same time. So I'm just going to go through a variety of examples. And I know you heard from one of my colleagues, Tim Rawson, yesterday. So you may have heard a little bit about some of this. And you've also got colleagues in the room who've also spoken at this program. So I want to flag to you the importance of connecting diagnostics with data collection and AI models. If we don't get the data from diagnostics, we are absolutely missing a huge wealth of data and also adequate representation. Now, we also need to understand that diagnostics are not just for therapeutic decision makings. They're not just, yes, you got it, no, you haven't, yes, you need this antibiotic, no, you don't. It's much more than that. They're used for screening, they're used for surveillance, they're used for monitoring. And we need to be able to get all of that data that we can, not just about the patient, livestock, environment, etc. But we also need to be able to get that in a way that we can use that data. And we need to get it from diagnostics that are cheap, effective and can be manufactured at scale. So smart, simple diagnostics, but their simplicity belies the phenomenal molecular medicine that is behind them, and how on earth we can actually use machine learning and AI to support the technology within those diagnostics. Also, the idea of point of care diagnostics, but also how we can apply AI to our existing diagnostics capabilities to make our diagnostic capabilities much more expansive. So this is a picture of my colleague Jesus Rodriguez Manzano, who many of you know, and he spent time with you in Uganda, and in also worked with colleagues looking and trialing rapid diagnostics for mpox in the field as well, who's developed some incredible diagnostic capabilities, and applying AI at the point of the molecular testing, but also then how can we generate that data so that we can then use it for interventions, monitoring, and developing new research questions. And this is opportunities within human health, but also in food production and livestock as well. So the next thing I want to talk about is not just the point of care diagnostics, but how we can use laboratory tests and all the data that they give to develop better fingerprints that can really expand our multiplexing capabilities. So we should not just look at PCR curves, we should look at the shape of them, we should look at the kinetics of them. And if we combine all this information about the shape, the speed, the kinetics, the nature of the curve, we can get much more out of our existing PCR platforms within our laboratories without adding any more machinery, but using the application of AI and all the data is not normally used, but is wasted and gives us much, much greater depth of understanding about the presence of organisms. So as I was talking about the importance of diagnostics and being able to do them at the point of care, as well as in the field, as well as in the laboratory. So here we're talking a little bit more about point of care technologies to generate data, and the phenomenal science that goes behind that. And why this is particularly important is this can also then develop databases and connectivity using whatever networks, but cloud-based opportunities to get not just a result at the point of care, but data at the point of care, geospatial tagging at the point of care, longitudinal follow-up. So quite extraordinary how, if we combine the science and the AI of diagnostics with the data generation, we have the most incredibly powerful tools. And here are some examples of a Dragonfly platform. I'm not going to go into it, but this is the most incredible technology that has all now been combined into a small rucksack. But it's being tested in farms, in livestock, in the Arctic for influenza, up mountains, I mentioned mpox already, for malaria, for COVID, but also for looking at wastewater. And I think, I mean, there's some beautiful work that comes out from Kampala around wastewater monitoring. And I think there's some incredible potential of linking some of that to some of the other potential data sources to inform us a little bit more about what's happening with antimicrobial resistance, with the management of wastewater, and also linking it to the impact of climate. So then a little bit more about lab-on-chip technology, and this is beautiful work supported by Damien Ming, a colleague, ex-PhD student of mine, and Nick Moser, who you saw in a photo earlier, who's a Google DeepMind fellow. And this is also about how we used artificial intelligence to manage dengue and the progression of dengue, which is a viral disease, particularly in Southeast Asia. And the thing about dengue is that it absolutely cripples healthcare systems because when it comes, it takes over all the beds within hospitals. It needs to be managed. The patients need to be managed appropriately. The progression to dengue shock in children means that you have to monitor carefully and do repeated hematocrits. And there's the most beautiful work, which has used AI to be able to use existing data, not anything fancy, existing data. And how can we predict progression to sepsis? But also, how can we use lab on a chip technology to not only diagnose whether it's dengue or not, but also what type of dengue? And then how can we use opportunities in non-invasive technology to monitor blood volume? And this has profound impact on how we monitor patients. So being able to process waveforms using pulse plethysmo, PPG, anyway, and how we can look at waveforms so that we're not continually taking hematocrit from small children is absolutely not only revolutionizing how we manage sick children with dengue, but also potentially how we can monitor and manage sepsis as well. So moving on from the really cool tech and the most incredible smart chip technology and the generation of data for AI, but also the generation of data to enable the most phenomenal diagnostics within the palm of your hand. I want to move you to the kind of reality of healthcare data and what a complete mess it is, how incredibly difficult it is to use health episode data, whether you have fancy electronic records or not. It's still really, really difficult to go beyond to make sense of a lot of healthcare data. And we need to understand that we can, of course, use artificial intelligence to help us with that, to help us match what's in the clinical coding, what's in the referral letters, what's in the generation of the codes, how can we link them? And also really importantly for us, how can we record this in terms of outcomes and also predicting usage and reflecting upon health economics and what it means. So the application of AI, particularly for us during COVID, enabled us to understand the real cost of co-infection within people infected with COVID. It was absolutely extraordinary. So during COVID, we also had, approximately 1 in 5 to 1 in 10 of the patients who developed COVID actually developed whilst they were in healthcare, whilst they were in hospitals for something else. That was where they got their COVID. And then for those people with COVID, the additional impact of getting a co-infection was very, very significant and buried under a whole load of data. And without the AI and the application of work of students such as Emma Carter, supported by Nina Zhu, who uses AI to help her with looking at the health economic impact of infection, we would not be able to do any of this. So I mentioned Nina before. So this is Nina Zhu, who many of you know, and she's worked particularly with colleagues in Uganda, looking at what the costs of the real costs and value of diagnostics are. But interestingly, we can also use AI to help us with the social representation of our patient populations to ensure that we capture representation of populations within our data set to make sure that we can absolutely capture that data. And this is a beautiful project with our colleagues in Brazil who also work with Andrew Kambuga and myself and our groups within Camonet. So I'm just wanting to flag that we should be thinking about AI in terms of how we can use it to ensure population representation and to help us make the health economic arguments to our policymakers and political leaders for them to take action. So this is now moving on a little bit from what Nina's doing to looking at health systems. I mean, it is absolutely crazy that we have designed health systems that are perfect biological systems to maximize the transmission and acquisition of organisms. If you had to design a way of bringing lots of infected people together, bringing them together, dispersing them, sharing, we have got that within our healthcare. And we need to look at our patient pathways, how we mix people up, how we use opportunities with vaccines to prevent and protect patient pathways more intelligently, how we understand pathways from the community into healthcare and back again, how we can think about how we protect the most vulnerable, how do we address people with burns, how do we address the seriously immunosuppressed, how can we target the way we protect them? How can we use and design our patient pathways? We need to be thinking about this much more than just seeing people and then shoving them into a bed somewhere in a crowded space. So we really missing the opportunity to look at the movement, the dynamics, not just the transmission and acquisition dynamics, not just the genomic dynamics, but the patient dynamics, and how we can layer this upon our data to understand how we can create pathways that minimize the transmission and acquisition, stop our healthcare from becoming a reservoir and an amplifier of antimicrobial resistance, but turn it into something that is well designed, ready to use the advances in immunotherapeutics, monoclonals, or just applying basic infection prevention and control and vaccines to maximize how we can protect patients, protect our healthcare, and develop resilience within our healthcare by using data intelligently to protect our patients and also to protect our staff and the running of our healthcare. So we're really missing a trick here by not applying AI at a systems level for ourselves. So you guys know so much about this, about storage of data and making sure that we have trusted environments for this. We're delighted to be working with Henry, who's on the panel here and is talking, and the phenomenal work he has been doing. And what a pleasure it is for him to have joined us in Liverpool and also to have seen him in Addis recently. So the importance of developing databases around how we can optimize dosing. So pharmacokinetic or PK data, how we can pull this together to inform how we can use antibiotics really effectively by having fantastic databases, not just small databases linked to industry that's not shared and doesn't represent huge parts of the population. We need to develop ways of being able to pool our data to inform how we can maximize the effectiveness of existing therapies and any that may potentially come along. But the pipeline is pretty dry. So we need this data so that we can absolutely maximize how we can use our existing PK data, pharmacokinetic data about antibiotics. And this little schemata above the Henry's paper that came out in Nature Communications around the need for a global data resource on this also shows work that we're doing at Imperial about making sure that we capture every therapeutic drug monitoring blood sample and integrate it with all the existing data about the patients to really, really test out the application of pooled data around therapeutic drug monitoring to maximize our personalized dosing opportunities and maximize the effectiveness of our existing agents. And it's not just maximizing the effectiveness, it's also minimizing the toxicity of them and making sure that we're dosing right in terms of other comorbidities people might have, and of course, other drugs that they may be on. And this is really beautiful work, and we are honored to be working with expert colleagues in IDI about this as well. So not only can we be using data to inform how we use antibiotics, we can also use data and artificial intelligence to help us analyze data and do surveillance and present it in a way that stakeholders want to see, presenting things in a way that's easy to initially recognize and take action and monitor. And I just wanted to flag that this is very nice work that some of our students are doing. And Oscar is a AI for Health PhD who's doing work with colleagues in India to see how they can do look at point prevalence surveys, but then go much further than point prevalence surveys and look at how can they use the hospital data to monitor healthcare acquired infections rather than using teams and teams of people to collect data. How can we use hospital data in real time? And it was really fantastic to be in Addis a little while ago and be hearing about what Africa CDC is doing in terms of point prevalence survey and how they're going to be able to pilot some of this type of work, perhaps in some countries, to see if they can use data in real time rather than doing a team-based data collection exercise in countries. So the opportunities to use real-time healthcare data to monitor healthcare-associated infection is something that's not only looked at in the UK, but now in India and potentially with Africa CDC. There's also a huge amount in clinical decision support. This is some work around how one can predict when's best to switch from IV to oral, but I suspect Tim Rawson mentioned some of that yesterday. But it also highlights why it's so critical that we work in a multi-professional way, working really closely with our pharmacists, as well as with our physicians, as well as with our experts in health data and in informatics. And I just want to go back now about, I mentioned about how we should be using the data we get with healthcare to apply artificial intelligence to understand where are we actually seeing the most transmission and acquisition. How can we then layer upon all of this movement data, patient dynamics, geospatial mapping, and layer upon it not only the organisms that go with the patient, the genomics of those organisms, both at the bacterial genome and plasmid level, but also the antibiotic exposure in different scenarios, at an individual and a group level. And this is applied in real time with COVID, using network analysis, particularly working with our incredible mathematicians. For instance, Maurizio Barahona, who supported Ash Mile during his PhD, working with Yuan, who many of our Cabinet colleagues know, who works in genomics. And how can we then layer upon the genomics and on top of this real-time mapping of patients? And that yielded some really interesting data in terms of where are we seeing the maximal transmission of carbapenemase producing enterobacterales. And also, not only where were we seeing the outbreaks, where could we predict they were happening, and how could we nip them in the bud by using this layer upon layer upon layer of data in an intelligent way. And this is work that we're only just touching upon now, and we should be doing this in real time. I mean, it is just absolutely incredible, you know, that hotels and airlines, although a bit of a problem now, but are able to monitor patient movements and then when people movement. But when we layer upon the organisms, the genomes, the AMR, the exposure, and in the background, other factors such as climate and other things going on, we have the most extraordinary capabilities, but we are just not applying them adequately at the moment. And just finally kind of moving on to, it's not just the data from the it's not just the data from the pathogens and the genomes that we're interested in. It's not just the data from people and populations. It's also the data about how policies work and what are the levers being used in policies and how can we use the data from national action plans to improve what countries are doing and monitor the effectiveness. So I think this is really interesting where we think about how we can use AI in influencing policy and learning from it and learning what works as well as what doesn't work. And this is the work of Rahila Ahmad, who many of you know, and also our colleague Rifat in Boston. But now I'm going to wrap up here with talking about, there was a time when we all shared data, well, at least some of us, and we worked together. And it is absolutely crucial that we do this and we support each other in doing this. I talked a lot about the role of diagnostics, both at the individual level and for the generating of data for public health at the national and international level. And it's really important that we sustain this and that we sustain this even in the absence of many, many of the funding mechanisms that are disappearing from the world. And one of the areas I have the privilege to be involved in is the launch of the Global Diagnostics Collaborative. It's a diagnostics collaborative to address antimicrobial resistance. But I just want to flag that any diagnostic that helps with the management of an infectious diseases or a febrile child or any febrile related disease helps one optimize how we treat the disease and how we use antimicrobials. So anything we can do about supporting and sustaining access to effective diagnostics and to advancing the scale up and the sustainability in terms of supply chains for them is absolutely critical globally. And this collaborative was launched in Accra in 2025, and it was a real pleasure to be there. The follow-up meeting is going to be hosted by Brazil next week. So if any of you are interested in that, please log on to those web links. And we need to find new ways to work that from the bottom up, that we work together as a collaborative or a coalition, but it is independent of any other organization. And we find ways to do this. So that's about diagnostics. But I also want to flag a meeting that I already mentioned, which took place in Addis just a little while ago. And it was fantastic to see Henry at that and also Isaac from Public Health. And this again was something that it was a real privilege to work with Africa CDC on this, that we need surveillance systems that we all sign up to with or without external organizations driving them, and that we need national buy-in to commit to these nationally, but also how we can work together to share data and advance this and find ways of doing this in a collaborative way, generating these alliances and new ways of working. So I'm going to end there, and I'm going to say thank you so much. I really wish I was in there in person. It's an absolute pleasure to be collaborating with you, and I think we're going to be doing a lot more of this in the future in a variety of ways. So back to you, Dowdy, and thank you so much for having me at this incredible meeting.
Thank you so much. Thank you so much, Alison. That was a brilliant, brilliant presentation. Exactly what we needed to sort of expose the participants here to the very diverse use cases of AI in AMR. And just hold the line, Alison. I think we're going to have some questions, some follow-up questions. And Rachel, I think, is moderating these. So any questions for Alison?
Thank you, Professor Alson, for the amazing presentation that you have just given to us. You have been talking about all these amazing things that AI is doing in the healthcare system. And one thing that caught my attention is the speed, the rate at which AI is really doing things compared to human hands. And my question is, what is your opinion about the health professions? Because what AI is doing now, we had people who were doing this work, and now AI is doing it in a minute. What will happen in the long run as far as AI and employment of these other professions in the health sector is concerned?
Two very challenging questions and two absolutely pertinent and wise questions. So the first one is about the speed and understanding, and the second one is about we're all going to be out of a job. Okay, so the first one about the speed, I think you're absolutely right, and the tension between the speed, but yet we haven't got the legislation and the regulatory frameworks that can cope with the speed. But we also haven't got a shared understanding. I mean, I think it's extraordinary that, you know, your students are designing things that, you know, your systems cannot even realize, but these incredible young people are in a new world, whereas the old world is still controlling it. And this mismatch is absolutely huge. Young populations, but older populations designing the systems is something that I think is a real challenge. And we need to have many more young people involved in how we design systems. But I also want to say something, though, about fundamental understanding. We have to be really careful. I'm not talking about the fundamental understanding of how the AI is working. I'm talking about the fundamental understanding of some of the principles of the science that goes into AI. And this is why we have to make sure that there's a deep understanding that is absolutely maintained, and that it cannot be AI alone. We have to make sure that people in the work that they do, although they're using the AI tools, that there has to be a group of people that maintain fundamental principles and knowledge. But I completely agree with you about where are we, you know, what's going to happen to our jobs? I mean, my goodness me. But we will still need people who've got fundamental understanding, and we will still need people who have a deep and complex understanding of real world issues. But you are absolutely right. I mean, what a threat it is. But we are going to depend on people who still know a lot about fundamental principles of science and arts and policy and humanities as well. I've no answer. I'm really sorry, but I'm grappling with the two things that you're raising, and also thinking about how we can teach far better.
Hello.
Hello.
Thank you for your presentation. And yesterday when we started, we had one of the core themes being reducing antibiotic use to fight antimicrobial resistance, which kind of sounds counterintuitive. But the question comes under these umbrellas that you've mentioned, it's like we are looking at these antimicrobial resistance just to kind of create much more better drugs to tackle this. And that is actually not answering one of the core themes of reducing the use, right?
No, I so disagree.
Okay, let me finish this last part of my question. And then you can answer them both.
Yeah.
Okay, and so my question is, under this umbrella, do we have people who are studying how these drugs and other drugs are interacting? Maybe that is leading to antimicrobial resistance, and the data was putting that at around between 20 to 30%. And so if we have people who are studying this drug-to-drug resistance, maybe then we can be able to knock out some of the drugs and perhaps maybe reduce the antibiotics we use. So that is the question. Like under these umbrellas, do you have specific groups of people that are studying these drug and drug reactions that contribute to AMR?
No, absolutely. I apologize. I apologize for interrupting your question, but I am am I allowed to? Brilliant. I can see your face now. Good. Why I was interrupting was because I feel so strongly that the amount of funding that's diverted to drug discovery is inappropriate, because there is so much that can be done by minimizing the use of antimicrobials to protect them, and protect them being effective by looking at how we prevent infections, how we minimize them from use of vaccines to infection prevention. So there are so many ways we can optimize the use and effectiveness and access to effectiveness beyond drug discovery. And that is why the network that Andrew Kambugu and I are part of, called the Centers of Antimicrobial Optimization, has got nothing to do with new drugs, because actually investing in new drugs only benefits a tiny proportion of the population. So we're really looking at how we optimize the use of antimicrobials and optimize their effectiveness. So that was why I very rudely interrupted, because I do not think new drugs are the answer. However, of course, we need to think about maintaining new drugs and keeping them going. And the artificial intelligence that is being applied to drug discovery is massive. I only touched upon it briefly in terms of the laboratory side, but it is massive, and you're absolutely right. There's a huge amount going on drug discovery. But you raised the issue about why don't we look at drug combinations and how they work together. And you happen to be, you've got Christine, Professor Christine there, and you've got the most incredible pharmacology unit at IDI, who is also looking into this issue. So you raised something really, really important about how can we look at how drugs work together and how can we apply artificial intelligence to that. And that is happening actually right now. And there is a funded body of work with colleagues looking at that. But you're spot on. How can we maximize the effectiveness by looking at combinations and the pharmacology of looking at combinations? So that is happening right now. But what I just wanted to stress is that we can do much more beyond drug discovery. And of course, the world needs new drugs. We need to keep up. But we will never be able to keep up with being able to share them with all across the world. And Darwinian evolution, which means every time something is exposed to something, we develop ways of getting around it. So brilliant idea about looking at drug combinations, and that is happening. But I just wanted to stress there's more that we can apply AI to than drug discovery. Thank you.
Thank you very much, Alison. You mentioned one of the opportunities is cross-domain integration. That means combining data at systems level. Could you give me some examples of successful integrations where AI has been applied at a systems level from your side? Thank you.
Yes, I'll give a really small example to illustrate that. But I was talking about the disease dengue and what you can do in terms of predicting likelihood of disease and hospital admissions and major surges into healthcare. And what's really important is that the tests you do at the patient level is highly dependent on seasonality. So combining the data around climate, seasons, along with what you're seeing in the patients gives far, far greater sensitivity and specificity to your diagnostic tools. So that's one example. And then there's also major opportunities that I was discussing about wanting to look at the combination of what's happening in the environment with what's happening in disease. There's a fascinating story about antifungal resistance, and fungal disease is really fungal disease is sometimes incredibly hard to treat, particularly in the vulnerable and immunosuppressed, and fungi are getting more and more resistant, and they're getting harder to treat in patients. But one of the reasons that we're seeing so much fungal disease that's resistant in patients is because of the exposure of crops to antifungals. So we're spraying our crops with antifungal medicine to stop the crops and the wheat from getting fungal disease. But this massive exposure and the monitoring of the exposure in the environment is linking to an understanding about why we're seeing terrible antifungal resistance in our patient population. So those are a couple of examples. There's a load more, but those are the ones on the top of my head.
Okay, thank you so much, Professor Alison. So mine is a question away from drug discovery. Like, is it possible for AI to predict resistance before it actually occurs, especially for coming strains?
Oh, that's also a great question. And at the meeting that Professor Jingo and I were just at in Sweden, it was absolutely incredible to see some of the work where they're applying exactly what you're saying, which is what are the early markers at the organism level of predicting resistance. But of course, it can be done not just at the single organism level. And we've been very interested in looking at a kind of population levels and in small population levels, such as small communities, such as in different wards or in different baby units and neonatal units, how you can absolutely predict by the level of exposure in that environment that the resistance developing. But at the molecular level, absolutely, it can be applied. But we're also quite excited about seeing it in real time with real organisms from individual patients. And the other thing that I think your question highlights is the importance of us not just looking at single time points, but if we're really wanting to understand things, we should have longitudinal data at the pathogen level, the genome level, the human response level, and at the drug level. And by combining the measurement of all of these, we'll have a much greater understanding and the capacity to predict much earlier. So, no, brilliant question. A lot being done there. But it's also really important that we have the capacity to be able to monitor this in real time and have dynamic data and not just static recordings.
Alison, we have a room full of questions, but we'll just cut it there. Thank you so much. That has been a very important and nourishing talk and answers to questions. We really appreciate the time you gave us and the time you took to get this presentation together. We're sure we'll be having you around next time. We totally understand you couldn't make it. So thank you so much. And that was the highlight of our keynote. I think we're now going to move into our next session. I don't know, Alison, if you have any final remarks or...
Just, I just want to congratulate you on the most extraordinary program. I'm really sorry, not just to be there to give my talk. I just thought the program was outstanding and I would have learned so much from being there. I wish I was there. What an extraordinary program, incredible people that you've brought together as well. And I look forward to working with you and hopefully seeing you again quite shortly.
Absolutely. Have a good one.
Bye, everybody.
Okay, that was such an insightful keynote address. We shall now move on to our oral presentations, where we're going to see various researchers contributing evidence and insights that can help advance the fight against antimicrobial resistance. So I'm going to call upon your names and you'll come and take a seat. So we have Justice Ohene Amofa. A round of applause as they come up. Next, we have Asindua Isaac. And our third person is Meshak Twea Omwega. No, first seat. So we shall do doing presentations in this order. So Justice Ohene Amofa is an applied bioinformatician at the Noguchi Memorial Institute for Medical Research, University of Ghana, working at the intersection of genomics, artificial intelligence, and public health. His research focuses on pathogen genomics, antimicrobial resistance surveillance, and the development of scalable bioinformatics pipelines for genomic data analysis. He also contributes to infectious disease genomic surveillance programs and supports bioinformatics training initiatives across Africa. Today, he will be presenting his work titled Leveraging AI in Optimized Detection of TB Infections Using Predictive Modeling with Multivariate Patient Data. And next, we shall have Asindua Isaac, who is a researcher at the Integrated Biorepository of H3 Africa, with interests in microbiology, molecular biology, and infectious disease research. His work focuses on antimicrobial resistance and translational laboratory science, and he was a second runner-up in the thermostable phytase enzyme design challenge at IDI/S Uganda. His research explores the antibacterial potential of Curcuma longa and Biden's pilosa against NDM1 and KPC2, producing bacterial strains. So his The title of the work he's presenting today is AI-driven optimization of natural compounds from curcuma longa and Bidens pilosa as novel inhibitors of beta-lactamase enzymes in drug-resistant bacteria. Our third presenter is Meshak Twea, who is a PhD student in microbiology at Kisii University and a PhD fellow at the Microbiology Hub Kericho Walter Reed Army Institute of Research. His research focuses on bacteriophage-based approaches to decolonize antimicrobial resistant Pseudomonas aeruginosa using genomic analysis, structure characterization, and AI-driven bioinformatics. He studies phage-host interactions. The title of the work he's presenting is From Genome to Therapeutic, AI-Guided Discovery of Phage-Lytic Proteins Against Multi-Drug Resistant Pseudomonas aeruginosa. So each of you will have 10 minutes to present. Justice, take the floor.
The movement.
The pointer. It's not that.
Sure. Okay. All right. I was going to say good morning, but then it's afternoon, so good afternoon, everyone. Yeah, so as you already know, my name is Justice Ohiniamufa, and I'll be presenting on the work titled Leveraging AI-Optimized TB Infections Using Deep Learning Predictive Modeling with Multivariate Patient Data. So this is quite the overview of what I'll be talking about, but then on a pertaining, I want to give you a welcome from also Ghana, especially for my institute, that's Noguchi Memorial Institute for Medical Research. All right, so TB is a disease of global concern, as you already know, and it's occurring largely in, especially in the Africa region. When you compare the diverse of how it's actually rapidly occurring in the state, you realize that it's happening more in more of the low resource settings. And you could see in a region like Ghana and other countries like that are all stationed in Africa, it's a lot more is happening, and there's more required work to be done in the early stages to prevent it than also before it gets to more of the happening stage. That is the early detection stage to engage in diagnostics before it gets so far. So on the background, you realize that TB, a lot of people have made publication on more TB happening news, on making celebrations on TB war days and all emergency programs. But the kind of question I want to ask is, what do we do to solve this canker that is actually proving so largely in our terrain? All right. So on that, my team and I, we decided to coin out a hypothesis to help in a diagnosis approach, and that is integrating a deep learning model that is going to have with the epidemiological and radiological findings with patient data. And that is actually the aim of what I'll be talking about. So on the specific objectives, it's going to enlighten on, going to create a model that is actually to help with the early detection rate, and also we're going to improve the precision rate of it, and also we're going to have it so we are going to have it so scalable to be free, to make users who want to actually access it be able to access it in free form. So let's quickly glance through the methodology. But before I go to the methodology, I want to give a quick disclaimer that the project is in phases. It's in 3 phases, and the first phase is what I'm presenting. I'll give you a bit of enlightenment towards the end about the large phase. So the first phase is what I actually gave you the idea pertaining to the PID and the radiological findings, and on the next phases, I'll actually give you an overview of what the current work that is ongoing between using to help with the identification of violence and evaluation, and also with respect to the evaluation and host response with explainable AI using biomarkers. So how do we collect our data? But before I give you a glance of our data, we had to actually get ethical clearance to using this patient's data for the work. So we got our ethical clearance from our institute, and we have an IRB, that's Institutional Review Board, that actually approved in using our data. And majority of our data set came from these organizations. That's the Kolebu Teaching Hospital. That's one of the biggest hospitals in Ghana, under the hospital of the MOH. That's the Ministry of Health, the Ghana Health Service, and also a private entity that's engaged in radiological finding. That is a Paradise Diagnosis Center located in La Paz. And with Cargo, I want to give the acknowledgement because we actually leverage on using their data as on scene data set to actually test our model to see how it's got. So in total, we're able to accumulate about 4,800 data sets, both in TB respective and TB positive and negative respective. And I made a glance in putting 540 there. The 540 simply means on the next phase of our project, we had 540 samples collected or pertaining to the data we already pre-collected to actually use it for the next phase of the project. That is the biomarkers approaches and also the explainable AI. All right, so I'll take you a glance to, I'll not go much about the workflow. This is how we went through with the workflow. We actually separated the data with the EPID approach and also with the imaging approaches, and we actually leverage on using RSNet, using the convolutional neural networks that actually did a max pooling of the images. And so we actually gathered the data in the approaches and using the metrics with the training set being 70 and actually the testing sets. And so upon all the approach, we were able to finish with the first stage and actually leverage the rest of the work on a streamlet that became the first phase of testing the interfaces. And so this is how the convolution, I'll give you a quick clue of how the convolution pooling, max pooling works. So it actually learns from a patterns of how the imaging are actually, so you have to feed it with some lines of code to actually feed on the patterns of the images, how you want to record, and how you want it to max pool all the images that looks like TB in the images, and with respect to the ones that are not also in TB. So it actually glances through the images, works through the patterns in all of them bit by bit to actually get them. And let's look at a quick about the results. So one part of the result that was fascinating was that max pooling was helping in the aspect of how the images were actually getting selected, especially in the H's of the image, the chest, especially because we are leveraging on the model on the chest to actually get it, because it shows how the image, both the X-rays, the X-ray images detected shows how the glance of how the chests are folded to show the depiction of how TB are occurring in those chest images. And we could see largely that there was a quick good score from the model that we actually got. And another one fascinating thing I want to actually add was convolution layers was actually helping us a lot, especially in this aspect. When you actually could zoom in a little bit, could see that there was a quite slice when we had to choose between using the max pooling and also the 2D pooling. When we, in that approach, we realized that the max pooling was actually trying in approaching broadening and giving a clear picture of how TB infected images were occurring rather than a 2D, which I'll quickly show you how it was looking at, which was quite, technically, I don't know the word to use, but then maybe not good to actually be presentable. So in that, we didn't end there. We had to compare it to other models that are pre-existing to make sure it is quite, good comparably to other models. And we realized that upon comparability, the other models were actually were performing in quite slightly better than the other models. But I think with the other models, the one that was quite close to us was the DZNet 160. But then I think RSNet was actually okay. So we tested it on an interface, which we are not, it's not out there yet because we want to actually customize the whole project on its faces and release it to all clinicians and all participants who engage in their work. And now, I'll give you the next clue quick about our next the next project we're talking about. That is about, so this actually the workflow the workflow we engaged in. So that is about the using of the biomarkers. So that's quite a workflow, but then I'll not explain quite. Once you have more time, you can actually talk about that. And we are actually going to embed on more of a mobile web, and so we quickly actually had a sample built, but then it's still, as I mentioned, it's still on our testing interfaces, and we would actually leverage on Duolingo. On future directions, we want to expand our data. We want to actually integrate more modal data sets to get the variety from various regions to know how our model tested. Because on the expense of using different biomarkers, you realize that different biomarkers give different clues of how your data looks like. And so we also want to, as I mentioned, with the mobile health application, and also improve all the other phases of the work. So in conclusion, if you haven't gotten anything with my presentation, I want to let you know that AI-driven diagnostics improve early detection. And I want to also know that this work is also in support with Ghana's national TB control strategy and also global goals. And so I want, these are kind of some of the resources and the packages that we leverage in our work. And I want to acknowledge the team from Noguchi and all those staff, and also the symposium organizers for giving me the chance to present the work. And these are the resources I used in presenting the slide. References, thank you.
Antimicrobial resistance is one of the leading reasons as to why most antibiotics today fail, because these, like antimicrobials or the enzymes that fight against our antibiotics, make it harder every day for the available antibiotics to perform their functions, as they degrade them, as they act as scissors or molecular shields that break down the antibiotics. Good afternoon. My name is Asindo Isaac. I'm here today to present or tell a story about a project that I did where I used AI-guided computational methods to design molecules that could help inhibit the action of like beta-lactamases from NDM1 and KP2C using ligands from Cucumber longa and Bidens pilosa. When you look at the numbers, according to Murray and Sartorius, in a paper they published in 2022 and 2023, they say like antimicrobial resistance caused about 1.27 million deaths in the world in the year 2019, but 1 million of these occurred in sub-Saharan Africa. As you can tell from the numbers from a paper that was published by Flaoshi, sub-Saharan Africa are those areas that have been colored red. You can see, like, for example, in our country, Uganda, we have a high rate of antimicrobial resistance. This can also be proved by a paper that was released by a School of Public Health last year in December, where about 47,000 Ugandans died of related AMR-associated deaths. But out of that, about 7,000, it was direct deaths. So these numbers are not just numbers, but they are real problems that cite that our health systems are failing, or the antibiotics that are being produced are failing, and there is pressure behind. So my project was in line with public health of the available data. So the NDM1, that's how they act. Like the bacteria how it prevents the antibiotics from performing the actions. They may prevent like entry into the cell, or when they enter the cell, they degrade them inside the cell. So my major interest was the kitchen spice and one annoying weed. When you look at them, they have, at their chemistry, they're made up of a lot of natural products. But my major interest was at curcumin in the cucumber longa, and also quercetin in the Bidens pilosa. And my major enzymes of interest was the NDM1 and the KP2C. NDM1 is the new daily metal beta enzyme, which is associated with capabinase resistance, and also the KPC is the hebicieli carbapenemase 2, which is also central in therapeutic failure. So my methodology was organized in a funnel-like way, where every step, it was about decisive measures, like reduce the worry that maybe what will be done. So first I did sequence retrieval from UniProt. I used UniProt because it was better than PDB. PDB gave me shorter sequences that were not like when you do sequence alignment and stuff, it wouldn't give you what you needed. So I did sequence retrieval from UniProt. That was very necessary for my reference enzymes. Then sequence alignment to see which regions of the enzymes are being kept throughout, like with other enzymes. You check along other sequences of NDM enzymes, KP2C, then you see which regions are conserved. Then you do structure prediction then to get the 3D molecule where we'll do docking. Then FP or pocket mapping to see where your ligands will bind. Then ligand preparation using PubChem, and that was majorly to get the ligand files of curcumin and the quercetin. Then you dock to see the binding, and also do the flexibility checks. So some of the results here, I'm not trying to prove beyond reasonable doubt that inhibition will occur, but I'm trying to get to the results to show how these results will, like how the molecule will bind, what are we going to do. So the first image, those are the results from the AlphaFold 2, trying to look at the PLD values to see which ones are the best. Then the other side, it's an image from Chimera to see our 3D structure of the enzyme that we are going to, and what are our places of interest. Then the other one is an autodoc image that you are trying to see how and where to improve in terms of binding and flexibility. So in the next image, you will see a graph and the docking values, then plus our final product. So the graph is to show that the molecule you have prepared, when you put it in the human body, it can do the inhibition under the normal body temperatures maintained. Then the docking, those values, the more negative is the more beauty of it. What is more interesting about it is that if you get a molecule, the binding with molecular residues, the natural residues, is the most interesting science about it. For Ugandans, that's not color yellow, it's color gold. Don't get annoyed. And that's our enzymes binding with a molecule that we had synthesized. So the molecule, the resultant molecule we got to, I called it a C-opt hybrid. It had a very good binding affinity with NDM1 of negative 10.4, which showed that it is really better than even it binds better. So when it comes to inhibition, it is really good. Then the negative 9.8, it was with the KP2C. The gene value, it was to show that the molecule we synthesized was flexible and stiff. Then at the end of the day, we came up with a stable candidate that was doing cross-class inhibition. One of the recommendations that I made, initially I didn't know this until, so I was going to behave like a Ugandan and blame the government. But I realized that in Makerere we actually have high performance computing. I didn't know that initially. And so we could do like more enzyme, like you go in the class of the enzymes, then you do the Bayesian theory stuff, such that you are doing like maybe a family of enzymes. Yeah, so thank you so much for giving me your ears. You've been good listeners, and I appreciate my friends like Yagen, Keats, and Brenda who helped me achieve this. Thank you so much. Could you please? So good afternoon. Yes, so my name is Meshak Twea from Kenya. I'm going to present to you an AI-guided discovery of phage lytic proteins against multi-drug resistant Pseudomonas aeruginosa. Yes, so MR is a problem, and it's more than 700,000 people die every day, and it's projected by the year 2050, more than 50 million people will die, and the burden will most likely be in Africa. And in Africa, the sub-Saharan Africa, we have limited research infrastructure, we have high cost of antibiotic discovery, and reliance of imported therapeutics. So we need to use alternatives. And the WHO has flagged the Caponemes Pseudomonas aeruginosa as a high priority pathogen. And so we need to use alternatives. And one of the promising alternatives is the use of bacteriophages. Bacteriophages are viruses that can kill bacteria. They inject the DNA into the bacteria. They use the bacteria as a host machinery to produce more viruses, and then it will burst the bacteria. So if it bursts the bacteria, that's what we want to harness in this research. And what it uses to burst the bacteria are enzymes. One example of the enzyme is an endolysin. But because phages are dynamic creatures, they have different lytic proteins that help them in killing these bacteria. So that's what I'm going to talk about today. So the study aim is to use the AI tools to discover therapeutic phage lytic proteins against this pathogen. And the study context is to use the proteins as standalone enzymatic antibiotics. We can use phages to kill bacteria, but most people are skeptical. How can I use a virus to treat me? And so before we sell that idea to you, we want to give an alternative than just injecting you with a virus, because a virus has a lot of things. If it goes into your body, there are some mutations that can happen, but that can be done in research. So the methodology pipeline is there's phage isolation. Phages are found in the sewage. Where bacteria is, phages are there. So they are natural predators to the bacteria. So where we have bacteria of interest, that's the bait where we'll have the viruses. So because, for example, the infections we go to the washrooms and we have the infections, so the sewages have the hub of these viruses. So the sewages as well, we go and hunt them. So we isolated 5 lytic bacteriophages from the Kenyan environment against this multi-drug Pseudomonas aeruginosa. These are clinical isolates that are circulating within Kenya.
So we had 5 unique bacteriophages, and then we did genomic sequencing of the genome of these phages using Illumina platform, and we did bioinformatics, and then we did protein annotation using a platform called Faroka pipeline. Then we went down to do protein identification of 5 distinct lytic proteins. One of them is anholin, second one is an endolysin, the spanins, and transglycosylases. And then from there, we did AlphaFold 3 predictions. And because we are injecting, if we want to use this phage, we want to use these proteins for human health, we had to also do immunogenicity and also docking. So these are the results. We had 2 unique phages. In the family FICMI viruses, we had 4 phages. In these 4 phages, all the lytic proteins had 100 sequence identity. So we only picked one protein from each. And then we also had a unique phage called a fixivirus. It's a very big, it's called a jumbo phage. It's a very big phage that has non-canonical mechanisms of killing bacteria. Non-canonical means they're a bit hypothetical. But if you blast their domains in the NCBI, you can find their homologs. And so the leading candidates, these are the proteins. I've coined them as LTE to represent endolysin. That's a coining. And so the leading candidates that I chose for downstream analysis was the endolysin and the transglycosylase because of their degrading catalytic activity. They are able to degrade the peptidoglycan layer of the cell, of the bacterial cell wall. So if you degrade the peptidoglycan layer of the bacterial cell wall, you have killed that bacteria. So we choose these 2 because of their degrading activity, and what we want to do, we want to use them as standalone antibacterial potential. They have standalone antibacterial potentials. So the next thing we do is AlphaFold 3. I was happy there was a mini, workshop on AlphaFold 3, and they taught us about these metrics, the BTM, the PLDT. And if you look at my protein here, most of it is blue. Most of the residuals are in the other blues, the very high confidence predictions. And then look at the expected position error, bit green, more darkened, yeah? So that means the accuracy of prediction in AlphaFold was high. And then that is AlphaFold doing its thing. But then we need to do external validation. So what I did, we used an endolysin from the uniplot, and we did what we call superimposing. And look at the root mean square deviation. It's below 1, 0.878 angstroms. That means it's accurate, it's on point. And then we also did what we call Ramachandran plots. Ramachandran plots measures the dihedral angles. So in the dihedral angles, all the residues, more than 96% residuals lied between the favored regions of the Ramachandran plots. That is still validating the confidence of AlphaFold prediction. And then we also, 88% of the residuals had PLDT of more than 90%. The same, that was an endolysin. These are transglycosylates, a very unique protein. Also the same, you can see most of it is dark and the metrics are a bit the same. So we went further to do immunogenicity analysis. We used an AI platform called NetMHC prediction. So in NetMHC prediction, it does T-cell epitope binders prediction. We don't want these proteins to bind, we don't want this protein to bind to alleles of the human population. So we used HLA alleles of the southern global population. So we had 7 HLA alleles for MHC2 strong binders. For MHC1, there was 0 binders for MHC2 strong binders. There was 6.1% for MHC1 strong binders, and there were 98 non-binders. That means it's mild immunogenicity. It cannot invoke inflammation if you inject that protein into a human being. The same as transglycosylase. It's a bit moderately not immunogenic. So The insight here is that Lytic E shows exceptional low immunogenicity and a rare and valuable property for therapeutic proteins. So if there is no immunogenicity, those are good therapeutic proteins. So we did these properties, and we found that the protein is stable. In mammalian reticulocytes, it's stable. And if you look at the molecular weight, it's optimal for recombinant production. So we also did docking with autodoc vena, and you can see the substrate, the NAGNAM, the N-acetyl, the complex of the peptidoglycan, the N-acetylmuramic acid and N-acetylglycemic acid had the highest binding affinities, and they show bacterial cell wall degradation properties. So the key findings here is the proteins that were predicted by AlphaFold and still modeled by autodoc vena, they add ultra low immunogenicity for the endolysins and the transglycosylases. They were stable proteins because of the instability index and the gravy index in mammalian half-life. And then they had high structural accuracy in AI, and they confirmed peptidoglycan binding. So the conclusion is we can use AI-based pipelines that can enable low-cost antimicrobial discovery from any other organism. And the next steps, because there was yesterday a coining that said, when you start, think of the end. So after this, we are supposed to do recombinant expression and purification of these proteins, and then we will do in vitro antibacterial testing against the clinical isolates of multi-drug resistant Pseudomonas aeruginosa in Kenya, and then determine their minimum inhibitory concentration, and then we will have a product that we can sell if all the ethical regulations pass. I acknowledge those people and the funding from the military of the US. Thank you.
Thank you very much, our presenters, for those wonderful presentations. We will have a Q&A. Any questions from the audience? Any questions? You can use the microphone on your desk.
Yes, so my question goes to Justice. So I have also worked with machine learning. I've built a machine learning model on using DenseNet. It was a clinical decision support system for fundus images. We analyzed fundus images, and we had different classes of the eye diseases. So I was analyzing early onset eye diseases. So I wanted to understand the nature of your data in the context of your output layer, what you used. So because I thought, since I have many classes of the eye diseases, I should use the softmax because it's a multi-class classification. But we found out that the sigmoid worked better for some reason. I think it analyzed the normal and the diseases each on its own. So I wanted to understand that.
Yes, please.
Okay, thank you very much, Kate. So this actually, we actually tested it on various theory models, and on the model approach, we leverage on using more of the sigmoid approach. That is because if you check the convol using the max pooling approach, you could see that the patterns were actually very clear on that. But if you use other layers to actually make the separation, it's not. So we leverage using the sigmoid approach. I don't know whether your question has been fully answered. Sure. Thanks.
Okay, Justice, right. Name. First speaker. You. Yeah, wonderful presentation, by the way. So I'm more focused on, because when you did the prototype for the mobile app, I noticed that you had it seems like it's a customer, like from a user's perspective, that the patients are the one that are. So I want to understand, how is the app intended to be used? And if you look at the research work you showed, you were working with scans, the X-ray scans and stuff. But in the app, I think I saw a place where they were to upload images. What is intended to be uploaded there? And then the last part will be how you intend to manage the cost of everything there, because it seems like you said something about it being open source and free for use and stuff. So how do you intend to manage it with regarding, the model and all those stuff?
Thank you very much for your thoughtful question. So the first I'll answer the pertaining with respect to the imaging. So with the mobile app application, it's in the testing phase, and that is for the whole, to cover for the whole project. You on the basis of the biomarkers. I think we could actually talk much more after stage. And well, with respect to the biomarkers, we actually I mentioned that we had the data of 540 from the same participant that we are leveraging to build a biomarker using a model through using biomarkers as the main optimal approach to actually making the detection. So in that approach, the patient would have to, or the user or the patient would have to upload their images either. So the main point of using the main focal on using the biomarker will be the eye. So we are testing on using a patient's eye rather than their sample, because they can submit samples online or something. You get it. So the main point is using the optical scanning approaches. So they would have to upload the image of the eye and actually will correlate on the basis of what the reports, the follow-up reports patient to be uploading regularly. So if you upload different images, it's not actually going to work for you on that approach. And the second question, I don't know whether can you go again with the second question?
It had to do with how you intend to maintain the cost.
Yes. So on the cost approach, yeah. So currently it's on seeding phases. So what I meant by seeding phases, it's a stepping stone to actually use to apply for a grant. I get it. So on the end, it's liaised with the Ministry of Health, and so it's supposed to be free for clinicians for use for testing. And once it's out, they can actually maybe on the approach they might accept on the third-party usage on getting on payment. But then for now, the whole idea on the motive is actually for free for clinicians and patients out there. Thank you.
Thank you all. Yes, the presentations were quite good, but I would like my question to go to Isaac Asindoa, I think. Yes. So one of the your choice of molecule is quercetin, but we know that quercetin is quite common in very many, very many of the greens, most of the vegetables, including onions. So later on, like at translational stage, how would you attribute your drug to be from Biden's pilosa and the other what's that? Okay, yeah, that herb, the turmeric. Yes. Like, how would you attribute that it is them actually that are performing this inhibitory effect and not the onions or the garlic and the greens that people are taking? Thank you.
Okay, thank you for that wonderful question. Initially, before I did the computational work of this project, I had done the wet lab, but the wet lab was concerning just the synergy when I combine the cucumber, the turmeric, and the blackjack. So I realized that at some point when I was doing the HPLC, that the quercetin had some had somewhere where it played a large role. But the translational part of it that you were talking about when maybe the research gets out, haven't yet explored that, and that's a good insight that I'll have to look into.
Okay, thank you very much. Any more questions? There is a who has a question? Someone?
Yes, yes. Congratulations to all presenters for the good presentation, but my question goes to Meshach. So Meshach, your predictions have been ended to molecular docking, and you are expecting to go for the in vitro assay. And as we know, molecular docking is not accounting for the flexibility of the complex. When you interact the compound with the receptor or the protein. So how are you sure that it's going to work for the biological system if you have been not predicting for the flexibility? Thank you.
You press the button.
Thank you so much. By using AlphaFold, it's just a validation. I just wanted the bind, whether the protein is able to bind to the substrate, and that's all I need. I don't think about the flexibility. The flexibility, it will be done in vitro. Remember the protein that I modeled. I'm not going to bioprint it exactly like this. I'm just going to use the sequences to produce the proteins, not the protein itself from the AlphaFold platform. Yes.
Okay, thank you very much. Before we move the mic, so again to you, Meshach.
Yes.
You mentioned in the abstract that, and you state, the discovery and evaluation of therapeutic lytic proteins from Kenyan bacteriophages.
Yes.
Could you help us appreciate how phages in Kenya are different from phages elsewhere, say in Uganda or?
It's because they are Kenyan, because they are specific. Remember, phages have specificity.
Can you classify phages by nationality?
But yes, you can classify phages by the nationality. Okay. Yeah, you should classify phages by nationality because the pathogens that are here the pathogens are here. The strains are different from the pathogens that could be in Kenya. If we find the similar one, then maybe we will classify it as Eastern African phages.
We shall leave that to the audience to discuss at lunch. Any more questions?
Yes.
Yes, please.
In computational biology, the reason we do computational biology is to make sure when we go to the wet lab is we are cutting the costs, right? And so Mr. Meshach is telling us that all he needed to do was to do a docking. Now, a docking score is not even a prediction of, it does not directly correlate to the binding affinity, unless of course it's an enthalpy play, which is mostly not. And we've not seen any GROMAX data of how, whether this thing is stable, and he wants us to move to a wet lab desk, which is going to put our money at risk. Of course, I'm not investing personally, but then I'm just worried for the person who's going to put his money there. So we've not seen GROMAX data, and you're telling us you're ready to move to wet lab studies. There's just a very big jump and leap of faith there that has not been accounted for as a computational biologist. And my second question goes to Justus. You said you're using sigmoid. So sigmoid basically plays a binary game, yeah? Zeros and ones. And so what happens when we increase the noise, the complexity, like maybe early stage, and then late stage, and then maybe middle stage, and then we throw in a bit of pneumonia data. So will we move from maybe sigmoid to something like a softmax? Show us early stage, maybe this is pneumonia, still shows that there is a presence of infection here, but slightly out of what we are looking for, and this is late stage, and stuff like that. Thank you.
Yes, please.
Yes, the reason why I think I am here, remember I'm not a bioinformatician, and I'm here to learn. And so I will look for you, and you guide me what to do next.
Okay. So thank you for that. And I want to add, to make a supplement to the previous question. So if the phages you are working with are unique to Kenya, wouldn't that limit your product to work only within Kenya? Is that the kind of product you'd want to put out?
When you're working on a product, you're working on a pipeline.
No.
So if you're working on a pipeline, the same pipeline can be used in Uganda.
No, the product, the phages for...
the product?
Yeah, the phages, the ones for for treating Pseudomonas aeruginosa.
Yes.
So if you're working with phages that are unique to Kenya,
yes,
doesn't that limit the effectiveness of your product to only Kenya? Because that's where you're only having.
Yes, because of its specificity. Then if it's working in Kenya, then it limits it so.
Okay,
yes.
Let us go to. Please answer your question from the audience.
Yes, thank you very much, Jagan. So, as I mentioned earlier on, we tested out with different models, especially using the DENS and using also the RSNet 160 and using UNet and VNet, all approaches. But with the CMOD, realized that you could see that the structure, the 2D images were appearing more quite clear and more, not more like the word is not, I don't know the particular word, but not so dense, so that it can make any, prediction that this is active. So, and apart from that, we make testing with all sorts of images that patient having cold or common cold or having pneumonia or having cancer to actually test on how the model relatively, work with. So, we make conclusion on a CMOD because it appears better and actually, but on the testing phase, I mentioned that we still use, there's going to much differ when you employ the use of larger data sets. And so we are going to employ the use of using larger data sets from Africa employing, and that is how it tests on variety of data and how your model feels on. I don't know whether I've answered your question fully. Quite. And okay, we'll see each other on backstage for talking. Thanks.
Justice, since you have the mic, I also have a question.
Thank you.
So your work is around developing predictive models for detecting TB infections, right? Did you bother to find out if there are other models already validated for this purpose?
Yes, thank you very much. So there were other models, as I mentioned earlier in the presentation, and we made comparisons to all the models in an approach. And the ideas behind this, there are crazy models out there, but the focal point was using it on the EPID features that we had with the patient data to make diagnosis early detections approach then, so that the patient can forego and go and get care or diagnosis on that and actually treat it early rather than waiting for it to actually get into a later stage where he can actually make a good treatment on that. So that is quite one of the goals on that. So the other models that were pre-existing, we make comparisons and I mentioned that they were slightly on average in equal, but one of the models that was outperforming best was the DenseNet 160, but it has the reason we didn't go the approach on the DenseNet 160 was that the images were still occluded and it could still predict an image that was TB as a pneumonia patient, which is actually not right. But on a scale of some points, getting a sharp images, it actually predicted on it. But the whole idea it's not to dance on not to depend on the images anymore, but we want to more focus on the biomarkers. That is actually the focal point on the work.
So if you talk about biomarkers, we know there are some already validated tests that are very easy to use. And do you think your models would be preferred to those tests, or?
So
because if I just run maybe a Nigra or whatever it may be, simple quick test, even just microscopy in itself, do you think one would prefer your models to those other already biomarker based tests?
So yeah, thank you very much. So to answer to your question, yes, a big yes, because we are looking on the last year of remote local settings who do not actually have the resources and the capabilities, especially if you visit some towns and villages. You could see you barely have the tools and resources to actually do a chest scan or actually do. But if you have one or two doctors who could actually assist patients on actually making checks on their health, on using just an eye scan, it's quite cheaper than actually going to have a full radiography imaging. It's not there to actually replace the whole process, but actually to help complement the efforts. Thank you.
Thank you very much. Any questions from the audience? I see the hands are still up. We still have some 10 or so minutes, so stay hooked. Maybe Walter, complimentary question or? Okay, 2 questions and we close. Be brief.
Yes, thank you. I'm going to be brief. So maybe to the last participant. So why maybe Andrew was asking you about why you focus on the phages is actually Kenyan is because like there's the lysis or the pathogenicity of these is usually more or less the same. So what is different about these Kenyan phages that is different from the rest of the world? And then later on, because you've done some characterization of the genome, you can, do a blast and see if maybe the proteins that you found in these phages are the same as the other side, then actually your I don't know whether it's a drug, I mean whatever you want to design using these phages can cut across. Yeah, that's just what I wanted to supplement.
Okay, that's a good comment. Walter, please, you can take note of that.
Yes, thank you very much, all our presenters. You actually presented quite amazing work. So my question goes to Ms. Irk. You are working on the proteins from the phage, and I saw at some point on your presentation, so you had one of the proteins, I think you predicted the structure using the AlphaFold, and you went ahead to actually align with the already, I think, experimental structure, right? Yeah, so we have been talking about AlphaFold throughout this symposium, and we know it's an AI tool which is predictive. So every structure we obtain from it is just a prediction. So I was wondering if you have the structure that's already experimentally designed, what could be the reason or what motivated you to go and again predict that you actually had the structure experimentally designed that you could go ahead and use? Could there be a particular reason why you did the prediction rather than using the experimental structure? Thank you.
So Isaac, take note of that. I think we can have that discussed at break, during the lunch break. And then also take note of, as you discover these compounds, whether they are from turmeric or whatever it is, could you try and compare their chemical structure with structures already active compounds for that particular, so that you can be able to gain insight on whether or the modes of drug resistance and that kind of stuff. All right, thank you very much. Our panelists, we have another session that is coming up. Yeah.
Yes, our next session before lunch is by Dr. Ronald Galiwango about the SAMR working group. Dr. Ronald Galiwango is a bioinformatics scientist and deputy director for the African Center of Excellence in Bioinformatics and Data Intensive Sciences. After earning first-class honors in mathematics and statistics from Makerere University in 2013, he received a Commonwealth Fellowship for a Master's in Philosophy in Computational Biology at the University of Cambridge in UK in 2014. In 2016, he pursued a PhD in Computational Epidemiology at the University of Georgia, USA, funded by a Fogarty NIH Fellowship, and enhanced his data science skills through DataCamp. His research focuses on applying quantitative methods, including bioinformatics, machine learning, and mathematical modeling, to address infectious disease challenges, with a particular emphasis on antimicrobial resistance. He has co-authored various peer-reviewed publications. He is a principal investigator, multi-PI, co-investigator, or a key personnel on various AMR, data science, infrastructure, and modeling and training grants. We welcome you, Dr. Galwango.
Hello, thanks, Gloria. Recognizing that I'm the one standing between you and your lunch, I'll try to be fast. So I'm going to walk you through some of what I believe is the impressive work that is being done by the members of the AMR working group. And I'll try to acknowledge them every time I mention someone's work. So maybe to start with, I'll just give you some context. So the African Center of Excellence in Bioinformatics and Data Intensive Sciences has that mission, which is to be a sustainable center of excellence that leverages high-performance computing, bioinformatics, health data science, enhanced visualization to support research and training that enhances health in Africa. And as you can see, we try to summarize the thematic areas in that graphic. But the reason why I wanted to show this is to show you that AMR is just one of the 4 core thematic areas under research that we do. And we have another one here that is related to it, which is malaria genomics and structural biology, but we have a full session for that. Maybe later on I'll just highlight some of the AMR aspects in that work. But we have a thematic area in AI and another one in human genomics. But those are for probably another symposium. So the research themes within the AMR working group are as follows. So we have building scalable and dynamic AMR data infrastructure. We also have development of data analytic platforms, as well as AMR at the One Health interface. I'll tell you more about that later. And then there's research which is looking at resistance in the human gut microbiome, as well as what you've heard about, which is drug repurposing, the so-called combination drug investigations group. I'll tell you more about that as well. And then, of course, AI and machine learning applications. Probably by now you're getting bored of hearing that term. And then lastly, which is often neglected as we are developing all these AI applications, there's that time of deployment and application in clinical settings. So we are very much thinking about that. Okay, so of course, some of this has been already presented, but I'll just add some context to it. So this is the tremendous work that is being done by our colleagues at the regional referral hospitals. You know, keeping all those files and having them stored for over, so many years for which the data was collected is actually a tremendous work. Now here we are saying maybe we can improve that process and maybe make it digitized. But it's important to acknowledge the important work that is being done by the regional referral hospitals and other hospitals, so to speak, in the country. So the challenge we are having is that most of the data that we need to work with is historical in nature, and that is the one that is mostly paper-based. Of course, government and the regional referral hospitals are implementing electronic medical records, but they're still siloed. And probably some work needs to be done in harmonizing and integrating them. And some of the data are messy, but not in the way that you think. They're messy in the form that the dispersion of these systems, makes them not communicating with each other. But also, clearly there is a lack of a data governance framework that can aid in the utilization of this data, not just saying don't touch it, but how can it be utilized responsibly? So that's where the idea of building a system that is interoperable, that can actually put together all these efforts that are being done by the clinicians and data officers and other clerks in the hospitals, comes in. So I'll just give you an example here of our study sites. So the thing I wanted to acknowledge is that this is a result of tremendous work, from Fleming Fund, Country Grant 1 and 2, that established the core infrastructure in these facilities to be able to do the antibiotic susceptibility testing and, do the other tests that are important for microbiology. And then, of course, thereafter, in Country Grant 2, there was work that was leading to doing all these surveys. Some of them are annual, others are quarterly, depending on whether the interest is in use or AMR. Of course, after that, we're just concluding the first phase of the Permanent project, which Professor Allison has expertly explained, and other speakers. And of course, she leads the Permanent Consortium, which was funded by Wellcome. So that specifically was looking at data on clinical outcomes. And of course, there came another daring project, which is funded by the Lacuna Fund and Wellcome, which was collecting additional data. So all those data are being put into a platform that is available to researchers and policymakers, but under a data governance framework. That is very important. It's not that because it's there, anyone can just utilize it. So you must have approvals in place to utilize that data. And the approvals are by the custodians of the data, Ministry of Health and others. Okay, so the end product is a dynamic data platform. Khalifan explained this expertly, but perhaps what he didn't tell you is that because the system was designed in a way that is modular in nature and also with the minding that we shall be using it for other platforms, we're actually now using such a platform to do the institutional-wide data governance, data platform, which we are calling HealthDB, which is already in place now. That incorporates HIV data, institutional program data, and other types of data. But it was all thanks to the work that was being done by Khalifan and other people. So a manuscript describing that work, I remember there was a question yesterday regarding if there's a description of the APIs and access procedures. All the things are being mentioned in that paper, and we're looking forward to it getting published. Okay, so once you develop the platforms, what next? So you can overlay, interesting things as well. Of course, within AMRDB we have, simple dashboards, but there are other initiatives in the AMR working group where individuals are looking at, in the existing data analysis platforms, mainly bioinformatics, how can we, make them intuitive, so that even people without the basic bioinformatics skills can actually maybe go on the web and do some simple analysis. So thanks to the work done by Deborah and others, of course, building on the work was done by Dr. Geraldine Bow and Ivan that developed RMAP 1 and also RMAP 2. So she has developed that platform that is easy to use. And she's around. Most of the people I'm talking about here are around, so in case you want to hear further. Yes, we have a lunch break. Okay, so of course, the recommended approach to AMR is via a One Health approach, because there is intersectoral defendability in terms of movement of, maybe AMR genes, for that say, from maybe the environment or from animals. I don't know about other countries, but at least I know in Uganda, there's a lot of antibiotics that are being used in, for example, animal feeds, poultry, and probably they shouldn't be used, but people are using them because they grow faster, and that is causing a problem. And this is actually what Carmonate and others are targeting, how we can stop the irresponsible use of those antibiotics. But focusing on her work, Patricia is looking at, how we can understand AMR that we are seeing in humans by looking at other sectors. And she has about 3 sub-studies that are looking at antibiotic use across the One Health domains that I've talked about, and then relating that to treatment guidelines, and then see if actually we can correlate what we are seeing in terms of resistance with the guidelines. And then thereafter, she's looking at the emergence and spread of ARGs in parasitic pathogens. Excuse me. So of course, it's actually very good to know what is happening now, but it's even better if we can predict what is going to happen tomorrow, because then we can do something about it. So lastly, she's looking at how we can predict AMR trends in humans, but looking at what is happening in animals and the environment. And speaking of One Health, there is tremendous work that is being done, or that has been done, in urban sewers in Kampala, thanks to the work done by Stephen and others, that was looking at metagenomics insights in the rhizostom in Kampala, wastewater. Again, in the interest of time, I'll be quick, but I can throw more light when we go over the lunch break. So there is other work that is happening. I've been talking about the macro scale, which is looking at the population dynamics. But now, what about what happens within us? So there's a fellow, Doreen, who is looking at AMR within the human gut microbiome, because we know there's a friendly bacteria in the gut that actually, under selection, can become something different. So she has 3 sub-studies that are actually looking at the characterization of those ARGs in the gut, but also looking at how resistance elements move between bacteria in the gut through horizontal gene transfer mechanisms. And also, finally, looking at the relationships between that and other dynamics. So most of the work I've been talking about here is for Uganda, but we have collaborations that span, Cameroon in the UK, but also recently we have a collaboration between us and NIH Cambodia that is looking at bacterial sequence types and AMR within that important region, Cambodia. So in case you don't know where Cambodia is, I just put a map there. But various scholars, like I've highlighted them there, they're looking at, trying to understand transmission of antimicrobial resistance, but also genetic diversity and evolutionary patterns of the different strains, both AMR and susceptible ones, in that region. And of course, Claire did tremendous work, and others, looking at drug repurposing, because like Professor Allison said, it may not be smart to look at developing new antibiotics. First of all, because the development time of a new antibiotic, from preclinical phase to clinical trials, and then to market approval, is around 15 years, give or take. Bacteria are learning new ways of evading those drugs. So why not use already existing ones that already been approved and see how we can optimize them? At least it has worked very well for HIV and cancer, so why not for AMR? So in this work, I want to highlight the first one there, where I think Claire is going to talk about this later on, but basically, we're just looking at how to combine all these different data sets and make meaningful contributions in terms of the predictions. But of course, there are other interesting studies that we are working on to get published as well, looking at even non-bacterial species like fungal infections. I'm highlighting here a publication gallery of the different works that are being done, ranging from bioinformatics, I've highlighted RMAP, of course, then the work under Camonate, and different PhD and master's students. I think I forgot to talk about this. So we have an ongoing master's and PhD program in bioinformatics, Anna Makere, but hosted at the S. So different students are working on different aspects of AMR, and we support them in our working group at the S. And actually, I think the call for applications is still running up until the end of the month. So if you're interested, please apply. So you can see the other different papers that I'm highlighting here, applying machine learning and AI tools, both collaborative and ones that are led by the S. So as I said, lastly, deployment is key, because if you develop all these tools and they're not translating to the clinical setting, it's like time wasted, because they do not influence anything. It's good to have all these cool publications, but what if the work we are doing actually influences policy, but also is taken up in the clinical setting? And one such illustration is what we did in the work that was sent to the AMR Vivly Challenge, where we were finalists, where we are looking at, where we developed a model for, predicting the risk of MDR. And then the most important thing is, on top of having a web platform which requires internet, we developed a platform that has, USSD, so you can use a small phone like mine to do some of the work without using internet. And this is important because, health workers, for example, in the rural areas, may not have access to internet, but they can still use the AI tools. So thanks to the work done by Claire, Shakira, Khalifan, and Henry. Of course, all that work wouldn't have been possible if it wasn't, the funding that we generously received from Google DeepMind and all the other funders that I'm highlighting there. Sorry, I've been rushing because I was standing between you and your lunch, but I welcome any questions. Thank you.
All right. Yes, it's time for questions. It's the opportunity to stand between us and lunch. Any questions? Okay. So we have some 2 questions here. Yes, briefly.
Thank you, Ronald and colleagues. I just have a brief comment or question. We are seeing a recent trend in relationship to AMR and climate change, especially regarding the droughts, the deforestation, the rain patterns, among others. Do you have some work done around that? Do you have some partners or collaborators in that area? Thank you.
Yes, please.
Okay, I'll go. Yes, so we just submitted, I think a few weeks back, a grant to Wellcome Trust to try to understand the relationship between climate and AMR, because largely, like I said, AMR is One Health. So even though it may not directly influence maybe disease, but through, for example, its effect on food systems and water security, it can actually influence AMR. So we actually submitted the grant. Maybe in the next symposium, I'll tell you about what we would have found if that work is funded.
Yes, thank you so much. My 2, and 1 is that maybe let me call it the last mile. After maybe the research is done and there is a project, now how do we roll it out? Any plans on sustaining the technologies that are going to be rolled out? Then 2, you talked about scholarships. So my inquiry is about how to get there. Thank you.
I'm not sure if I talked about scholarships, but that's a nice way of asking for one. Yeah, so I was saying the program, applications, call for applications is out for individuals interested in enrolling in the bioinformatics program. But usually, of course, there are external funders. So sometimes if there's a scholarship, for example, like the ones we had under our Sheet Data Science program, those are advertised. So look out for our social media platforms and see if there are any opportunities. But also, usually within Makerere, there are individuals who fund our students. So also look out for the Makerere socials. So regarding sustainability, our sustainability is in terms of, like what I've just showed you in the AMR DB, where we build onto that and put it within other working groups. But also in terms of actual implementation, our plan is to, for example, maybe in other projects, maybe the second phase of Kamane, to try and pilot these platforms that we've developed in a clinical setting and see what happens. Maybe clinical trials later on, but to start with, we want to see if we tested it with, for example, one of the regional referral hospitals, will it actually improve patient outcomes? Yes, I don't know if I've answered your question. Thank you.
Yeah, thank you, Ronald, for the wonderful presentation. You've been doing some great work. My first question is, are there opportunities for one to join the AMR working group, and how do they join? Then the second question is, you've talked about the AMR data that you've been able to collect over the years. If someone is doing some work in the area of AMR, are they in position to access the data, and how can they be able to access it? Thank you.
Yes, I'll start with the last one. So the AMR DB platform is up and running, and all you have to do is to request for access. So you go to one of the, I think you go to the main page and then click request for access, and then there's a team that reviews, your request. Then regarding joining the AMR working group, I think I saw Patricia somewhere. She's seated there. She's the coordinator for that working group. Of course, as long as your passion is AMR and you're doing some AMR work and you're willing to invest some hours a week, you're welcome to the group.
Thank you very much, Ronald. A round of applause for Ronald. Finally, he has released us for lunch. Unfortunately, Shahid is still holding us here. So he has a small communication. After that, we go for lunch.
I can use this. Yes, good afternoon, everyone. Thank you so much for keeping up to this time. Just 2 communications, we go for lunch. One, we still have poster sessions at lunchtime. Due to public demand, we decided to push them to include them in the lunch schedule. So when you finish your meal, please pass by and get to learn more before the session is closed up at the end of lunchtime. The second communication is that for those who have other activities, please hang around up to the end of the day. We still have a few presentations to come in. We have a lot of goodies coming up in the evening, souvenirs for everyone attending, and we don't want to keep them. So please hang around so that you go when you have fully taken up the entire day and all the planned activities. Thank you so much. We can go for lunch.
you.
I look professional? Button. Oh my god, I don't want to button. Mama, does the button look good? Hey, strings. Okay, let me button, but I'll button more than one. Okay. Should I smile or say what? Is this thing on? Okay.
That's your hidden.
Afternoon, waliyo panel.
Gloria Danga. Alex. Welcome back from lunch. The owner of vehicle number UBL 464Z, green in color, you're requested to go and clear away for others to park. UBL 464Z, green in color.
Good afternoon. Good afternoon. We first of all welcome back from lunch. I hope you enjoyed the break. We are going to start the afternoon session. At this juncture, allow me to welcome Dr. Daudi Jingo, the director of the African Centers of Excellence in Bioinformatics and Data Intensive Sciences. Dr. Jingo serves as the director of the African Center of Excellence in Bioinformatics and Data Intensive Sciences, whose mandate involves providing cutting-edge computational platforms, hardware, software, and research expertise for biological research. He is a senior lecturer in the Department of Computer Science at Makerere University and the principal investigator of various research and training programs that apply bioinformatics, data science, and generative AI. His research interests cut across human genomics, cancer genomics, and antimicrobial resistance. He earned his PhD in bioinformatics as a Fulbright scholar at the Georgia Institute of Technology in Atlanta, United States of America. He preceded that with a master's in bioinformatics and computational biology from the University of Leeds in the UK, and a Bachelor of Science in biochemistry from Makerere University here in Uganda, where you are right now. He previously served as a bioinformatics consultant for the United States Centers for Disease Control, commonly known as CDC, in Atlanta. Dr. Jingo, we welcome you to give us this talk.
So, good afternoon once again. And I'm here to just give a talk on antimicrobial resistance, which happens in what you would call in another orbit. Because we've been talking about antimicrobial resistance mostly in the context of bacteria and to some extent viruses, but mostly in the context of bacteria. But what we want to look at now is, this is on, okay, good. Yes, so what we want to look at now is to look at drug resistance in a more complex organism, especially in parasites, because it plays out slightly differently, as we're going to see. So this is mostly in the context of malaria. And of course, I don't need to belabor the extent to which malaria is a burden to all populations around the world, but especially to our populations here in Africa, because we have about 95% of the malaria burden. So we have a very abiding interest in knowing what goes on there. And of course, the predominant parasite that is responsible for malaria in Africa is P. falciparum, which is that worm-like parasite that you see there. When you look at it, it's actually a very simple organism. It doesn't have ears, nose, eyes. It's really, it even looks less complex than a worm because you don't see any features except the single structure that it is. But the thing is that that parasite is very very complex. And if I was speaking human language, I would say that it is very clever. Because as you can see, it's a very, I don't know if I'm able to point. As you can see on the bottom left, where you see the mosquito, is that it has adapted itself to living in multiple environments. So it lives in the human and lives in the mosquito. Imagine yourself if you could, I don't know, live in the ocean and also live on land. That is how complex this organism is. And what you see on the right is the many different forms that it takes on to be able to survive in those different environments. I think you're seeing about 12 different life stages, some of which are very different from the others. So again, if you're a human, you could imagine yourself if at one point of your life you are a bird, and then at some point you're a worm, and then at some point you're a human. That is what this parasite does. So it is actually a very complex organism. And it has perfected that art because it has lived with us for a very, very, very long time. You know, actually, as a parasite, it was around before humans were around. And when we arrived on the scene, it just adapted to living with humans, and it has perfected that. And so, eventually, when we thought ourselves clever enough to invent drugs, it also figured out solutions. And I think I won't go a lot into this detail, but I think Dr. Arakira covered some of this yesterday, the different mechanisms at a proteomic level that this organism adapts to in order to be resistant to drugs. Most of them are, of course, driven by mutations, but those mutations can either be at a metabolic level where it metabolizes the drug differently, the malaria drug, it could metabolize it differently, or not metabolize it at all, or it could just pump it out of, you take the drugs, and once they enter the cells, the thing just pumps them out, so that before they do any damage, and so on and so forth. So it has adapted in so many different ways to drugs, and therefore is also a problem in drug resistance. So, because it's very complex, in some ways we are limited by traditional approaches to research, including, you know, laboratory assays, and the inability to detect emerging mutations because there are no good laboratory assays to do that. But also because the parasite itself has a very complex population structure. In other words, you know, you have so many different strains of it distributed differently and under different types of pressures. So, I think we have used quite a bit of bioinformatics in malaria for some time, but I think AI is a new injection. I remember many years ago writing a paper on ligand binding hotspots of malaria, published in Infections and Biology in South Africa. But I think AI is giving us a new lease of life in terms of how to approach this very recalcitrant parasite, and being able to detect resistance at the earliest possible stage. First of all, We need it because, of course, like I said, it's a very complex parasite. So the blue graphs show the comparative size of the malaria genome and the TB genome. So the short blue bar is the TB genome, and the big blue is the malaria genome. So you can see, even if everything else were constant, just the very basic level of this biology means that this thing is a lot of work. So if you use 5 units of energy to figure out things in TB, you'll need orders of magnitude to figure out the same thing in malaria, just by the size alone, before we talk about all the other complexities. So it's a very unusual genome, which also adapts quickly, it mutates quickly, and also is difficult to sequence. I think there are a few people here who do malaria that I see in the area. It's also a difficult genome to sequence because it has a lot of repeats, as we're going to see. So of course it mutates quickly, and that is, mutation is driven by the environment, as we know. And because this thing goes through a very complex life cycle, it subjects itself to so many different environments, and therefore it's much more likely to mutate because it has more selection pressure happening on it, as opposed to TB, for example, which might be in your lungs and maybe in your brain for certain variants of it. This thing, as we saw, exists in so many different stages and is therefore that complex. So it is AT-rich. That means it has a lot of repetitive regions. In most genomes, when you see a lot of ATs as opposed to C and Gs, that means it's repetitive regions. And so it kind of like has a lot of a genomic scrapyard from which it can adapt or collect new ways of behavior. Like some of the high organisms, it also has very diverse gene families. And also, it's not easy to assemble, of course, because of the repeats that it has, the many repetitive sequences that it has. So that means that when you look at all that level of complexity, it means that there's very likely that you'll get some help by looking at AI as one point of recourse. So one of the things, some of the ways that we have already seen is 3 generations of treatment to malaria, which this thing has figured out. So when I grew up, malaria was being treated mostly by chloroquine. I don't know if you guys ever had chloroquine, but it was this drug which, if you had it, first of all, it caused a lot of nightmares. For real. Like if you had chloroquine, at night you dream all sorts of things. So it's kind of a psychotic, apart from being an anti-malaria, it's also a kind of psychotic, it had psychotic effects. But anyway, through acquiring mutations in those 3 different genomes, genes, PF-CRT, that is Plasmodium falciparum CRT, and then MDR1, and a few others, it figured out a way around that. So we then moved to sulfadoxine, pyrimethamine, and then it figured out answers around that too, through mutations in DHPS and DHPFR. And now for the last several years, about 10 years or so, we've been very dependent on artemisins. And it's beginning to figure out solutions around that, to acquire mutations that confer it resistance, especially in the PFK13. There's a lot of research in Uganda here which is seeing resistance to this emerging, especially in the northeastern part of the country. So these are all very different genes in very different locations of the parasite, but it's like whatever solution you bring up, it looks in the entire spectrum of the parasite and figures out where to do its magic. So you're really looking at a case of millions of genetic variants. You're having to look at large population data sets because there are so many people in different individuals and different samples of the parasite, and really thousands of parasite genomes. So it's almost a landscape where you really are not going to have a lot of success by doing standard classical experimental biology. You definitely have to look at recourse in AI. Because apart from all those different levels of complexity, you have to look at them at all these different stages. You're looking at the genomics, you're looking at the transcriptomics, you're looking at the proteomics, the structural biology, you're looking at even behavior, population behavior, and so on and so forth. So, but if you have recourse to AI, then you're able to at least find some way, shape or form of prioritizing. First of all, predicting and prioritizing these perturbations, identifying novel SNPs or emerging mutations, and even having some insights into parasite fitness. So that means that, of course, you look into some of the tools, and we've been talking about AlphaFold all day, but there are so many other tools at the different levels, both at the structural level, at the genomic level, but even at the PK, pharmacokinetics, pharmacodynamics level. There are so many different tools you can look at. But at least one of the things that something like AlphaFold give us, it's giving us some level of targetedness. And as you saw the presentation by Akrut in the morning and Warakia, and those who have attended the AlphaFold workshops before, there's a whole lot of science behind that, a lot of AI science behind a tool like AlphaFold. But what it does for us is to be able to point to us specific areas where to look. You know, when you predict the 3D conformations of these proteins, and then you're able to see where the ligands are binding or where the active spots are, at least that reduces the problem space that you have to look at. And therefore, if you're talking about compute, for example, it reduces the compute power that you need. For people who have not done a lot of work in this space, that might seem mundane, but compute power is a real problem. It's almost like if you're working in a laboratory and you don't have money for reagents. If you don't have money for, I don't know, for chloroquine, for pH, to change pH, you can't carry out experiments. You simply cannot. Or if you're going to sequence and you don't have PCR reagents and so on, you can't sequence. So this is a literal problem. There are so many people in this room who will tell you their research is stuck because either they don't have access to the right resources, or if they have the access to the resources, they're a bit slow, or they have been cut out and now they want to have access again. I don't know if Kawadia is in the room, but there are so many people here. So compute is a real problem, and to the extent that you can cut down the amount of compute that you require to solve a certain problem, it really is a real significant benefit. And this is partly what these tools do for us. The ability to be able to look at protein-protein interactions, that means know where to look. The ability to execute deep learning algorithms. If we had our lecture would have a look at how deep learning, what they call deep learning. There's a computer science student, I think he has left he's trying to run away from a deep learning course. And I told him it's a very bad idea at this time. Anyway, so AI would help us do that. And we are very, very, very lucky, which is a very odd thing to say because having malaria is not a good thing, or having these diseases. But at least it puts us in a unique place to be the ones to answer these questions because we are the ones who are having to contend with these problems. Having the highest malaria burden and having all these malaria genomes being sequenced. I think Shahid Shiaga is in the room. He's here, yes. He just led a program where he sequenced hundreds of malaria genomes, and that's, by the way, on the entire continent is a new thing. And of course, we're beginning to have this computational infrastructure, the HPC, and so very soon we're going to be able to do AI-driven malaria surveillance, and aspects of that are beginning, and therefore be able to tackle malaria almost in the same way that we would tackle cancer, with levels of precision which have really not been done before, because malaria is still treated as a generic thing. There's like 3 drugs or 1 drug, and everybody is treated with those, and so on and so forth. But there's a whole area of precision medicine in malaria. But we're only not there because we've not had recourse to tools like AI. And hopefully that's an area where we're going to have to apply those tools. And so everybody's realizing this, and at least Google Research, which is a branch of Google, as you know, by the way, Google for many years did work mostly in the computing space. But luckily now they're branching into the biomedical space because there's a lot to be learned there, and which is also impactful. But the whole idea is to maximize human ingenuity using AI tools. And when we talk about human ingenuity, we're really talking about the heads in this room. There's a Senegalese guy who talks about it like that, like there are all these brains in this room. Each brain is capable of so many different things, but then you have to give it the right tools, the right skills and the right tools, and that is what programs like this are looking at. How do we amplify the ingenuity in all of your heads, in all of our heads as we are in this room? Because each of us can think of so many different things to do that. And where we're starting with this is a project called AIMA, also in collaboration with Google Research, where we're trying to look at, to use AI to scale both the pace and accuracy with which we can investigate malaria, drug resistance in malaria. A lot of work, as you know, in malaria has been mostly GWAS type based, where you study and look for variations that are associated with different aspects of malaria, like resistance, like immune evasion. But with this specific project, it's very intentional in applying AI to look at scale, at so many variants and so many traits, especially resistance to different drugs, but also immune evasion. So that then we're able to have, it's like a zoomed out look at this parasite and seeing the entire landscape of pertinent mutations that are pertinent to resistance and that are pertinent to immune evasion, and in many ways getting some insight into the mechanisms by which they do this. Because, as you said, if you're using AlphaFold and similar tools, it's actually pointing you to very specific locations on a protein. And therefore, that gives you insights into the mechanistic approaches of the parasite. And so, we hope that we'll be able to discover polygenic resistance markers, and that is through integrating genomics and structural biology, and hopefully being able to predict next generation resistant mutations, and also having insights through vaccines and drug in this kind of work. So the take home is that drug resistance is, of course, a big threat to malaria control. Imagine if we woke up tomorrow and the drugs that we use to treat malaria only work 20%. You literally begin having your friends drop dead. So it's a real serious problem. And all this resistance, like we were told yesterday, is driven by mutations, which especially those that impact the proteome of the malaria. So, and we want to use AI for all these approaches here, large-scale analysis of parasites, discover resistance markers, identification of new drug targets, and faster translation of genomic data. So, yeah, thank you. I know that was a bit meandering, but it is it is to look at, beyond the bacteria, there are all these other parasitic species and these other disease propagators and pathogens and so on. We really know nothing about all those things, and it is going to be you guys to figure that out. Once you get a hand on how to use these tools, and also you understand the biology behind the diseases so that you can meaningfully and appropriately apply the tools. Thank you.
Thank you very much, Dr. Jingo, for that insightful presentation. 2 questions from the audience, maybe 3. Khalifan.
Hello, thanks for the presentation. I just wanted to ask, what causes the mutation? Is it the misuse of drugs, or are they just complex?
Yes, Khalifan, that's a very, very good question. What causes the mutation? And at least it shows that people are thinking about, because I've just been talking about mutations as if they appear from heaven. That's a very good question. The thing is that I think Professor Alison Holmes mentioned Darwinian theory in her talk. So the only reason we live as living organisms, as individuals, as persons, but also as any living organism, is because every time our bodies are challenged, they figure out solutions. And that is not because they're inherently intelligent, but because you constantly have mutations that happen in your body. And this is not just people, but any organism. They constantly have mutations. Those mutations happen randomly. Most of them are mistakes when the gene is being transcribed or read. Sometimes you get mistakes. As you would make a mistake while you're writing the letter and you forget to copy one letter or you misspell a word. So even the transcriptional mechanisms in our bodies, or in the bodies of living things, when they're copying your DNA to make a new copy, they're literally copying like you would copy. They copy letter A for A, T for T, and sometimes they make mistakes. So those mistakes are what we call mutations, and they arise spontaneously. It means they arise constantly but spontaneously. Now, sometimes those mutations, most of the time, they cause bad things to happen because they're mutations. But once in a while, they cause good things to happen. So for the malaria parasite, like all parasites, it constantly has mutations happening. Not by design, not by anything, but just as mistakes. But once in a while, those mutations give them the ability to survive a drug or to resist a drug. And because they do that, the parasites that have that mistake end up surviving. And eventually they dominate the population because they're the ones that are surviving. So that is how these mutations arise. Very good question.
Thank you very much, Dr. Jingo.
Thank you, Dr. Jingo, for that beautiful presentation. Please, my question is touching the AI tool, the use of AI tools in treating malarias. I begin to have some biased mind concerning the use of AI. You know, now, some of the patients, they are now on their own, as in using self-medication, because they have this tool around them. So they can easily make use of this tool to find which drug can I use to treat myself on this malaria, something like that. Is this AI not introducing self-medication to the system? That's my question. Thank you.
Thank you very much, Dr. Low. And I have some answers, but actually the guy sitting next to you is a malaria specialist. I'm going to request him to explain that. Because he's been out in the field and he has interacted with people who have malaria and treatment and so on.
Yes, indeed, the more we access these tools, the more information we have at our disposal. And yes, in some instances, I mean, people Google, you know, now they talk of Dr. Google. Yeah, yeah. I mean, but that is a totally different docket altogether. You know, but in this particular scenario, we are not developing a tool that is accessed by patients, but rather we are applying AI, yeah, to mine data to study the parasite in finer detail. Yeah, the patients do not actually get access to this for this particular project. Yeah, thank you.
Thank you, Dr. Lo. Good question.
Thank you for the wonderful talk. I have two questions. One is, given the reduced use of the previously used antimalarials, do you think that maybe using them now might be, maybe they could work again, like chloroquine that have not been used in many places for a long time? Do you think that now that they haven't been used for a long time, they might work again if they were used? The other one is, do you think that maybe making new drugs making new antimalarial drugs is the way through or towards fighting malaria, or do we have to just use the drugs that we already have better, because the resistance keeps coming even when we find new drugs? Thank you.
Very, 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 very good question. And I think parts of that came up during Professor Allison's talk. Yeah, and part of the point she made is that maybe what we need to do is to figure out better management of these drugs. So it's a multi-pronged solution. So there is definitely value in new medications, without a doubt, because if we have resistance to some medications, then having new medications solves part of the problem. But as Professor Allison pointed out, is that there is even a bigger impact to be achieved if we manage these existing drugs better, in the way that we prescribe them and in the way that we avoid overusage of those drugs. So that because the reason AMR arises, the reason drug resistance arises is because we misuse the drugs. We administer them when we shouldn't, or we take them and once we feel the headache is gone, we stop taking them. Whereas the bug is still there in our body, and then it gets the opportunity to mutate. Whereas if you took your full dose, by the way, I hope people in this room take their full doses when the doctors prescribe. Most people, once they feel like they can jump again, they're like, I don't want to look at those tablets again. Those are the issues that raise drug resistance, and it's where we need to, it's part of where we need to look. So I fully agree, management and better use of the drugs is a huge part of the solution.
Thank you very much, Dr. Jingo, for that presentation.
There's some people behind you, but I don't know if we have time.
Be brief. We shall take on the one.
Okay, and thank you very much. My question goes, okay, most people who suffer from malaria or who have frequent cases of malaria also have other conditions, maybe like TB or HIV and many others. And these are diseases that have issues to do with what? Drug resistance. So that's the solution we are developing also help to look at compatibility for people in such scenarios, drug compatibility.
Thank you. I think Dr. Alakira will help with that also.
So are you talking about co-infections, malaria co-infections? Or So there are a few drugs that cut across, but oftentimes you'll find that the drug is most effective for what it was prescribed for. But ultimately, once you're applying suboptimal drug pressure, whether knowingly or unknowingly, yeah, for a particular bug, then you are exposing or you are pushing it towards developing resistance. Yeah, you get what I mean? For example, if you have, I don't want to be very specific, but if you have disease A and disease B at the same time, and then you're taking drugs for disease A, but those drugs suboptimally act on the pathogen for disease B. Yeah, so ideally you're supposed to be treated for both diseases at the same time. You get what I mean? No, in this case we are studying specifically malaria. Yeah, we are not studying it as we are not studying co-infections, because remember you can have so many combinations. If you have to look at co-infections, like the space becomes big and becomes infeasible to study. All right, thank you very much. Another round of applause for Dr. Jingo for the wonderful presentation. You can always meet with him for further questions. I know that it's a very interesting subject. At this point, I would like to invite Shahid Chiaga to take us to the next session. Shahid is a malariologist. He's a bioinformatician. He works at the African Centers of Excellence in Bioinformatics and Data Intensive Sciences at the S. He's highly experienced in malaria genomics. He will tell you more about himself when he gets up here. Thank you.
Thank you, Dr. Walakila. Good afternoon, everyone. Yes, I wouldn't want to repeat my names, but I'm Shahid. Preferably, I prefer one name, even though I have more than one. So everyone just calls me Shahid, that's it. But I'm Shahid Chiaga. I'm a bioinformatician. I do data science. I'm a teacher. I'm a researcher. I'm a mentor in the field of bioinformatics. So basically, that's me. I'm going to take you through the next session, which is early career researcher session. So we are going to have a couple of early career scientists. These are people who are walking into the footsteps of our doctors and professors. They are just behind them trying to achieve where they are. And they are going to share with us a lot of innovative approaches that they are applying using artificial intelligence, genomic surveillance, bioinformatics platforms, and policy analysis in AMR. So each presenter will be given about 10 minutes to make a presentation, after which we shall have a discussion between you interacting with them. All right? Through me, obviously. All right. So the first presenter is Mr. Mike Nsubuga. Mr. Nsubuga is a research fellow at the African Center of Excellence in Bioinformatics in Uganda, working at the intersection of digital health, clinical research, and data science. His work focuses on developing digital health technologies, including mobile health applications, and working with clinicians to enhance clinical and genomic data for research and healthcare delivery in low-resource settings. His current research centers on antimicrobial resistance, where he applies bioinformatics and machine learning to understand the genomic determinants of resistance, virulence, and pathogen evolution. Mike is an MRC-funded PhD student at the University of Bristol in UK, where he is collaborating with the UK Health Security Agency to develop machine learning approaches for forecasting airborne, foodborne disease outbreaks and identifying genomic mechanisms of AMR. He is currently a visiting PhD student at the Imperial College of London through the GW4 MRC Broadening Horizons program. He's working with Professor Leonid to benchmark machine learning models for AMR prediction using the largest curated AMR genotype phenotype database. You're welcome, Mike. The next early career researcher is Mr. Henry Mutegeki. Henry is a software engineer and an AI researcher specializing in machine learning for healthcare. He recently completed a master's degree in computer science, specializing in AI and data science at Makerere University as a Google DeepMind scholar. His research interests revolve around interpretable machine learning, multimodal AI, and data-driven clinical decision support systems for resource-constrained healthcare systems. Henry has worked on projects including emergency department triage prediction, malaria detection, and antimicrobial resistance prediction from clinical data. Alongside his research, he has vast software engineering experience at the African Center of Excellence in Bioinformatics and Data Intensive Sciences, S. Uganda, where he supports software development and system administration, maintaining a high-performance computing cluster and contributing to the development of health data systems, such as the Epilepsy Smart App and the Sickle Cell Pan-African Registry, SPARCO. He currently leads the Camonet Global Data Repository Initiative, focused on curating global antimicrobial resistance data into a secure, centralized platform to accelerate AMR research. You are welcome, Mr. Henry Mutegeki. Thank you. Our third presenter or discussant is going to be Ms. Oliver Nalumansi. Ms. Oliver Nalumansi is a pharmacist with a Master of Science in Bioinformatics from Makerere University. She has interests in antimicrobial resistance genomics and data-driven infectious diseases research. Her work focuses on genomic analysis of multi-drug-resistant Escherichia coli, particularly the role of mobile genetic elements in the transmission of resistance genes. She's interested in applying bioinformatics and emerging artificial intelligence approaches to strengthen AMR surveillance, precision medicine, and public health in resource-limited settings. You're welcome, Ms. Oliver Nalumansi. The fourth panelist is Ms. Deborah Neumbe. Deborah is a bioinformatics researcher with a master's in bioinformatics from Makerere University. Her work focuses on genomic analysis of bacterial pathogens and antimicrobial resistance. She developed the ARAMAP web, a web-based platform that enables accessible genomic AMR analysis workflows. Deborah is interested in applying bioinformatics to strengthen bacterial genomic surveillance and AMR research in Africa. You're welcome, Deborah. The fifth panelist is Ms. Patricia Nabisubi. Patricia is a bioinformatician and infectious diseases modeler based at African Center of Excellence in Bioinformatics and Data Intensive Sciences and at the Infectious Diseases Institute, Makerere University, Uganda. She holds a bachelor's degree in biomedical laboratory technology and a master's degree in bioinformatics and is currently pursuing her PhD with the support from the Sheet Data Science Initiative, abbreviation SHADES. Patricia's work focuses broadly on antimicrobial resistance, genomic epidemiology, and the application of bioinformatics, artificial intelligence, and mathematical modeling to understand infectious diseases dynamics. Beyond her research, she's actively engaged with scientific collaboration and capacity building across Africa. She coordinates the Mathematical Modeling Research Group and the Antimicrobial Resistance Research Group at the S. Patricia is a member of several international scientific communities, including the African Society of Biomathematics, the Public Health Alliance for Genomic Epidemiology, the GF4GH, Women for One Health, and R-Ladies. Ladies who do R. Yes. This is where she contributes to initiatives that promote open science, computational training, and inclusive research networks. You're welcome, Patricia. And our final panelist is Miss Rachel Claire Chomukama. Claire is a master's fellow in bioinformatics at Makerere University with a keen interest in addressing biomedical research questions using data-driven approaches. Her research focuses on leveraging data science techniques to combat AMR. She's a member of the combination drug investigation group called Coding at the African Center of Excellence in Bioinformatics and Data Intensive Sciences, Uganda, where she employs in silico methods to design and identify synergistic drug combination against pathogenic microorganisms. You're welcome, Ms. Claire Rachel Chomkama. Thank you so much. These are the panelists. We have 6 panelists, and they are going to have 10 minutes each, starting from Mr. Mike Nsubuga, to have a presentation. And after all of them have finished their presentations, then we shall have a discussion. So please keep noting questions. We are going to have a thorough discussion. Mike Nsubuga, you're welcome. Thank you so much.
Thank you, Shahid. Yes, thank you, Shahid, for that warm introduction. So my name is Mike Nsubuga, and I'm a PhD student. And the work that I'm going to be presenting is part of the work that I'm doing during my PhD, which is around utilizing machine learning for tracing gastrointestinal outbreaks and AMR. So to give you a bit of a background, I'm working on a pathogen called Salmonella, which most of you may already be aware of. So Salmonella is a leading cause of gastroenteritis, and it's also the most commonly reported non-typhoidal Salmonella cerevisiae in the UK. It's been involved in so many outbreaks. It's always involved in outbreaks, especially outbreaks which are related to food. But you know, like what I mean by that is if you traveled abroad, the way I have done here, if I was to go back to the UK and I had a food illness, there is a high chance that it's either going to be one of the usual suspects, Salmonella and E. coli. So during such outbreaks, the UK HSA, which is the UK Health Security Agency, I think the equivalent of that would be the Ministry of Health. I think we have a department of pandemic response and outbreaks. So what they do is they do track these outbreaks and they do respond to alert the public. And they use quite a couple of tools, and they do a lot of genomics to, one, detect where are these cases coming from, but also to sort of monitor these cases. The systems that they use do work very, 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 very well. They are quite very clever systems. They're quite simplistic, but also they are quite very clever. They do something called SNP address typing, which technically means is they'll compare clusters of cases which are related. So if I was to have a case of Salmonella, they'll take a sample from me and then they'll compare it within their databases, and then they will see if it's related or similar to other cases that they have. And if it is similar to the cases, there's a high chance it will be from East Africa, and then they'll pinpoint that it's from East Africa. Fine. But the issue is, it does take quite some time, and there are also some times when it doesn't capture everything. So my research is revolving around using machine learning to reduce the time from detecting these outbreaks to finding the source where the outbreaks are coming from. But also as I do that, then there is also AMR, which I won't make any further introduction to it. Most of the speakers have made. So there's a lot going on this slide, so don't worry or focus a lot. But basically, it's an overview of the data set that I have been working on. So the UK HSA has curated. So they do routine sequencing of these cases whenever they happen. And they've been collecting these Salmonellas. Not only Salmonella, they've also been collecting other pathogens, but I'm interested in Salmonella. And they've been doing it for the last 10 years. Now, one other thing that they do collect, which you need to remember, and which is also going to be very, very relevant to this talk, is, when they visit a patient who is having a case of a pathogen, they also record where they traveled to, if they have traveled. As I said, this sort of, this bag is quite associated with travel. So panel A, in the corner, what you see are some of the countries where people do travel quite often. And I think you may not see clearly, but Uganda is also there. And they've been doing this for the last 10 years. I'm going to zoom in on, so what we've done, we've looked at the genomic sort of structure. So what we are trying to do is we're trying to build models, machine learning models, which can pinpoint, provide it a genome or a sequencer, and then it will tell you with confidence that this person, or this bug is originating from Spain or South Africa, name it. So we've done some bit of population structure to understand the data, and I'm just going to zoom in on one of the figures here, which is the one at the bottom, to sort of make a point. So this plot is showing the sampling effort, or the number of samples, and also it's showing the diversity. So the y-axis is showing the diversity, which is the lineages in the data, and then also the number of samples as they increase. So what we've done is we've got all the countries, and then we've clustered them based on the region. So if, I think you can see Eastern Africa, that means it will be a cluster of all the samples that are coming from East Africa, and so on and so forth. So as you can see, there is a linear relationship, which is already expected. So the more samples you collect, the more the more diversity you are going to see in the data. And that's sort of very clear, and it will be expected. But the other thing that is also interesting is this relationship sort of plateaus at some point, meaning that there comes a point whereby no matter how many samples you are collecting, there is nothing that you are adding to the diversity. And this is very, very important for the machine learning models. Now, one thing that is clear from here, I have used an example of the Caribbeans, which is a country, I don't have a pointer, but it's having 10 lineages, and we do have a lot of samples from the Caribbean. Now, one thing that we can already tell before even doing any fancy machine learning is our models are going to easily detect regions from the Caribbean. Because one, if we are seeing low genetic diversity, it could mean that maybe the cases we are dealing with are quite very local. Then the other thing also it tells us is, then on the other end, places like Southern Europe, the one at the top, which is having over 30 lineages, now that already shows it's going to be very problematic for the models, because they're going to have to deal with quite a lot of things, okay? And then the other thing as well is for the low countries, like, there's Southern Africa here, there's Australia, New Zealand, we have fewer data. Again, before doing any machine learning, I know that I won't be capturing much. So this is really, really useful for data scientists, because I think there is always a case of let's pump more data to these models. And I think some speakers yesterday did also highlight some of this, like, bacteria data is always very, very biased. I won't go into detail a lot on this slide. What it's really doing is sort of the presence of resistance in these sort of travelers. There's quite a lot of stuff coming in, within Northern Africa and Asia, okay? And then to dive into that population structure, there are two stories here. The first one is there's a lineage which is, it's not sort of resistant, but it's spreading internationally. So these bar plots, if you just look at only one of them, if you look at the one, the one which is part C, those colors are countries, so it shows that it started within, let's say, 4 countries, and it's been expanding over time, which is quite sort of interesting. And then there is also another lineage, which is multi-drug resistance associated. So what that means is we've got some colors, the tips on the tree, the one sort of close to the bottom, that dark bluish color. So that's from Egypt. It's from Northern Africa. I know it's from Egypt. And then you've got others from Eastern Asia and so on and so forth. And you don't need to be some sort of a phylogenic expert or even to understand a lot. But what's happening is there is quite lots of resistance genes, different ones, which each of these clades or sublineages are capturing. Now, again, before I do machine learning, I can pretty much know that the problem that I have, which is trying to predict the source of the countries, here we see that there is a relationship in the data where actually the AMR or the resistance can help us to, capture that, okay? So can we detect the source of these outbreaks using machine learning? Quick answer is yes, because there is a signal that we can quantify in the data. So this is a phylogeny, and this is our data. Africa is in yellow. There are sort of clusters all over the place. It's sort of a simplified figure. In reality, it's not as simple as this, because sometimes you do have, countries mixing up all over the place. I won't go into the details of that, but if there is a quantifiable signal, it means we can actually capture that sort of data. So that's, for now, that's all I'll present. I won't go into the details of the machine learning work that I'm currently doing. And then this is my team at Bristol. It's sort of a collaborative work. And then the other thing I want to mention, so I'm currently on a PhD break, and I'm visiting Imperial, where I'm working with a very, very, very brilliant team of people. And I want to bring this resource to all of you, because one thing that has been clear in all the talks is data, lots of fragmented data. So what these guys have done, they have collated all the AMR data, like all the data in all the well-known databases. You've got Patrick and a couple of other databases, and they have collaborated with EBI, and they are hosting this data together with the phenotypes, okay? And they have also built a very, very clever pipeline which scans a publication and it picks the data from it. So this database also has data from publications. So if you post your paper with the data, there is a high chance it will also be included in this database. So in total, they have over 170,000 genomes and over 1.8 million entries of drug phenotype sort of comparisons. And in the next slide, this is just an example. You can literally sort of sort by Uganda, and you're able to just download this data. They've sort of got the MIC values also as well. So they've got also the MIC, and also they've got the sort of the binary classes and the breakpoints and the way how this data was collected. It's a really, really, really very, very useful resource that I recommend to everyone. So what am I doing at this place? So I'm getting that entire data set, which is I think one of the largest, and I'm building a benchmarking of how, so I'm building a benchmarking of how each model is going to work, or to put it lightly, some of the speakers, what they said yesterday, and which is true, is bacteria are very, very complicated. Like you move from one bacteria and then it gets very complicated. You get from MTB to E. coli or Salmonella, and all of a sudden you can't capture the resistance using the same method that you are using. So if you went online and you looked at some of the papers, including mine, there is a high chance that someone will have picked a pathogen and then they would have represented this data, maybe SNPs. Now the problem with bacteria is you can't capture everything through SNPs. For example, if you're sort of considering things like bacteria which have open pangenomes or closed pangenomes like TB. So the way you represent the data sort of matters, and also the way you also evaluate it. So what we are doing is we are sort of building a benchmark to see what works for each species and also in which format. So it's a very, very, very huge project with loads and loads of data. So yeah, thank you for that.
Thank you so much, Mike. That was a wonderful presentation about cabbage, and I saw everyone taking a picture of the cabbage database. I'm sure they're going to add in a lot of data, probably by the end of the week. Yes, Henry, go ahead.
Thank you, Shahid. Yeah, my name is Henry Mitigiki, as introduced, and I'll be presenting my work on interpretable machine learning for multi-drug resistance prediction in UTI patients. And this was an extract from my master's thesis, from which I recently graduated. Looking at UTIs, they are a common infection, and they account to over 40% of hospital-acquired infections, and these tally to up to 150 million infections annually, globally, and which accounts to a very big health care crisis. And statistics show that 1 in 2 women will suffer from UTIs, with even a high possibility of reoccurrence throughout their lifetime. But treating these UTI infections is made much more complicated with the existence of AMR, where the antibiotics for UTIs evade or mutate such that they can no longer kill the bacteria. And as we have seen over the past 1 or 2 days, if current trends go on, AMR is likely to be the leading cause of death by 2050, surpassing diseases like cancer. So what we see here is, we have UTI infections that are getting worsened by AMR, and we need to do something about it. But to paint this picture is a scenario where you are a patient, you have a UTI infection. This is what your first 72 hours will look like. So hour 0, you have arrived, a urine sample is taken off you for lab analysis, and then from hour 1 to hour 48, a culture and sensitivity test is done, or whole genome sequencing in some cases. And then probably by hour 72, which is day 3, that's when you can get definitive results of whether you're resistant or sensitive to the antibiotics available. So what we see here is a blind spot of the time between which we shall know whether you're resistant. And this is about 3 days. And between these 3 days, doctors, the condition is getting worse, so the doctors are forced into using empirical methods, that is educated guesses of, since you have this UTI, it has worked for many people, this antibiotic has worked for many people, so start on this as we wait for results. But these empirical guesses actually lead to more and more resistance because they are not based on the resistance profile of the person or on the individual. So one may ask, surely can it really get worse from this? And yeah, sorry to disappoint that it can actually get worse. So with the existence of multi-drug resistant pathogens like E. coli that cause these UTI infections, we are seeing AMR evolving from just AMR resistance to one antibiotic, and it's now translating to MDR, which is multi-drug resistance, whereby the pathogens are not just evading one drug, but they're now evading a whole army of drugs across different antibiotic classes. And so, it's leading to a bigger crisis than we actually thought we have. But yeah, we have AI. And of course, in every story, there's a hero. And in this case, AI comes in and saves the day. And through AI, we can be able to study the patterns, given patient medical history, on your prior antibiotic use, other comorbidities that you've had in the past. Can we use AI, build models, and understand the patterns within patients that have had similar characteristics, but also known resistance profiles, to predict whether or not they will likely exhibit multi-drug resistant pathogens. So the approach is really to utilize electronic health records that have been collected over a period of time, and then train machine learning models, evaluate them, and with the goal of eventually deploying them. So we went on into sourcing for data, a rich data set, which we arrived at, and it had over 100,000 patient records from about 2 hospitals in the US. That's Massachusetts General Hospital and Birmingham Women's Hospital, and they had over 700 plus variables, and they were looking at 4 antibiotics that are used to treat UTI, and this was got from Physionet, so it's a good data source for anyone wanting to do more research in that line. So the methodology was clear. We had the data. So what we did feature selection, handling missing values, and also addressing class imbalance. But before we go to the model training, we also did what we call feature engineering. So the basic data that we had was resistance profiles across these 4 antibiotics. But then we had to define what multi-drug resistance means within our data set. So if you have 4 antibiotics, and then you have either a 0 or 1, meaning resistant or susceptible, how do you define multi-drug resistance? So, and we know the definition is when it's resistant to 2 or more classes of antibiotics. So we did write some scripts that generate a new category called MDR, whereby if you have resistance for one patient, if you have resistance to 2 or more antibiotics within your row, we categorize you as MDR. If you have resistance to only 1, then you're single drug resistance, and if you had none, then you're non-resistant. So we had 3 classes, and then it now turned into a machine learning problem, which led us into the modeling, and we built both traditional machine learning and deep learning algorithms to evaluate how they perform on this problem, and also did hyperparameter tuning to improve the performance of the models. We also did evaluation of these models. So briefly, for the machine learning models, they generally performed better across the charts compared to their deep learning counterparts, and this was consistent with existing research because the data was wholly tabular in nature, and they could easily figure their way around the patterns within this data, but notably the boosting algorithms performed really well. That's the histogram gradient boost, XG boost, cut boost, and random forest performed really well. But maybe interestingly, that something I came across was when we tried to fuse these models, whereby we get a deep learning model and also get a machine learning model, and then build a stacked model which includes 3 of them, maybe 2 machine learning, 1 deep learning. We noticed that there was an improvement in the performance of the deep learning models across the board. So that's something that some of the researchers can take up and explore in their research. So beyond just building the models, really wanted to answer the question of how is the machine learning model arriving to these predictions, and that takes us into the world of interpretability, because most of the models that we build are black box, so you don't know what's really going on, but you have a good answer. So we used explainable techniques like SHARP and LIME to try and dig into how the model arrives from an input to an output. And what we found is, some of the major indicators of, the risk of MDR are, if a patient had frequent visits to the emergency department, the likelihood of them developing MDR was really high. But also things like prior antibiotic use would greatly affect, this resistance. But an interesting one was education. It came up as an interesting variable as a predictor to MDR. And when I did more research on it and explored literature, I found that how well people know about use of antibiotics, but also the education that we get kind of shapes our behavior within the society. So you find that the common thing is you self-prescribe. You feel some sort of flu, cough, you just go pick up any antibiotics. But the more the higher we get educated and learn more on these topics, it drives behavioral change. So I anticipate that's why such a variable was really coming up top. So such interpretability information helps us to build models that are transparent and can be trusted. And with trust comes easy adoption within the healthcare system. And most health workers will tell you that the biggest barrier to taking up the machine learning models that we build is because they don't know how they arrive at those predictions that they make. So once we include the aspect of trust, we're really bringing our models that we build closer to the real world. So looking forward, some of the things that we look to do is one, how can we move from just the modeling to application, bringing this to the real world? That is through things like deployment and seeing how this works, but also increasing the global representation of the data through the different antimicrobial stewardship programs, but also knowing that the vast amount of data available is really from either US, UK, or Europe in general. So if we can increase the representation, we can have models that are more fair to us. So in the end, the goal is to make sure that UTIs never become a death sentence to us by having machine learning help us in predicting the different behaviors. I would like to thank my supervisors, Dr. Daudi and Dr. Ronald, and my DeepMind mentor, Dr. Jack Danger, and Google DeepMind for funding my master's. Thank you so much.
Thank you so much, Henry. Yes, Oliver.
Good afternoon or good evening. My name is Nadumansi Oliver, and I'll be presenting my study that I did concerning bacterial sequence types, antimicrobial resistance determinants, and mobilome of drug-resistant E. coli clinical isolates from Cambodia. Maybe before I start off, I would like to let you know that this was birthed out of collaboration between S Uganda and NIH Cambodia. Sorry, Dr. Rahman? All right. As some presenters have noted or have already talked about a little bit of E. coli, it's a gram-negative bacteria, and usually it's harmless, commonly found in normal flora, in our intestines or in the intestines of animals. However, over time, this bacteria has evolved, and some strains or some of them have acquired some virulence factors that have enabled them to be pathogenic. Now, if they are pathogenic, sometimes they can cause us infections, and the infections may vary in terms of effects on us, from mild infections to life-threatening ones. Of course, treatment also varies depending on how serious. If it's mild, it can just be supportive, but as we go upwards to severe, now we have to introduce antibiotics to help us combat this organism. But now we have a problem, AMR, and Cambodia is no exception to this problem, and recently it has been worsened by drug resistant, as the former presenter has also hinted on it. But in my case, or according to WHO, will define drug resistance as resistance to more than 3 classes of antibiotics, or at least one drug in more than 3 classes of antibiotics. Now, usually this resistance there's so many things that drive it, but one of the culprits is the mobile genetic elements. And like the plasmids, people are talking about phages, we have the transposomes. So it tends to drive this resistance, in that now the resistance is not passed from parent to offspring, but it is horizontal. The plasmid can just get out of the bacteria and then invade another bacteria in a very short time. So our research or our study came in mostly to try to understand the genetic mechanisms driving these increased levels of resistance in Cambodia. Our study basically involved, we had a mother study before done in Cambodia. What they've done in Cambodia recently, around 2021 to 22, there was an increase in a surge of gram-negative infections or patients that were hospitalized, and on investigations, it was gram-negative pathogens that were the culprits. So what they decided to do aggressively was now to incorporate genomic surveillance in their normal AMR surveillance. And then what they did, they went to different hospitals across the country, collected samples, did bacterial isolation, and then did sequencing at a centralized laboratory, and then uploaded the sequences in NCBI. So we got the sequences. Of course, with collaboration with them, we got the sequences and tried to collaborate with them so that we help them also understand the situation better genetically, or genomically rather. So we got the sequences, downloaded them, of course, did using bioinformatic tools, different bioinformatics tools. We did quality control, of course, on the data first before we went further downstream. And then we assembled our reads, did quality control, and then it was after these assemblies that we did the different analyses that helped us understand the sequence types, the AMR genes involved, and the mobile genetic elements. And this is what we found. So the E. coli population in our database was basically made of 24 distinct strains. So which means that we have a population that's highly diverse, but mainly dominated by a strain, a very common strain called ST131, and followed by ST1193. And then for the AMR genetic landscape, it was quite interesting. On the extreme, I'm so poor with hands because I'm left-handed, but on the left-hand side, we have a heat map that shows a gene, AMR gene presence and absence. So on the bottom, we have the x-axis that shows the exact genes, but to make it easier for you, we put it in blocks. Vertically, each block represents an antibiotic class. Then horizontally, each block represents a strain type, a different strain at any one time. So definitely from our heat map, you can clearly see that the strains we are dealing with are indeed mild-drug resistance, because you're having so many blocks that are densely populated or densely colored. Then on my right-hand side, the extreme right, we also have the prevalence by antibiotic class. And from these strains, we can tell that we have strains 100%, all of them resistant to a certain gene resistant to beta-lactams. And then we have also co-resistance to aminoglycosides and sulfonamides. So it was highly likely that you could find a strain that's resistant, that has a gene against beta-lactams, which usually are the first-line agents in managing E. coli, but then that same strain also carries resistance to an aminoglycoside, and it also carries resistance to a sulfonamide. But also macrolide resistance was also present, and resistance to tetracyclines and etc. Resistance to carbapenems, which are usually last-line drugs. Now, previous presenters told us the rate at which people are making drug discovery is a little slower now compared to how it was back in the day. So that's why people are putting together efforts to try to find other means to combat AMR. So now, the situation is, yes, resistant towards carbapenems and polymyxins, it's rare, but it's scary, because these are our last lines, and if we are having our strain starting to be resistant, we have to be cautious and then move into action before it gets out of hand. Also, we went ahead now to the mobile genetic elements. Our concentration was on plasmids, transposomes, insertion sequences, bacteriophages, and I think I've mentioned transposons. There were 5 that we concentrated on, which are usually the most common. So obviously, plasmids were found in all our genomes, but we also went ahead to detect, like, apart from detecting that plasmids are common, and we've also detected that this strain has this gene. Is this gene carried by a plasmid? So we went ahead to verify plasmid carriage of these AMR genes, and we found that plasmid carriage of AMR genes is actually common. And then IS elements, they are in almost all our genomes. They are actually in all our genomes, but since they are very, very small elements, they're just a transposable element, just keeps facilitating other genes to move around or to insert themselves. So it's hard to find an AMR gene located within an AS element. But transposomes, which are quite wide, we found some, and it was really rare. We only found one genome with a bacteriophage that was carrying acquired resistance genes. So what does this mean? So the AMR landscape in Cambodia is really dominated by high-risk global strains, which are ST131 and ST1193. And these particular strains, apart from having a big landscape in Cambodia, they are also carrying multi-drug resistance to so many drugs. And basically, their resistance is mainly driven by mobile genetic elements, especially the plasmids. The transposomes and the bacteriophages could be playing just a supportive role, since the coverage of AMR in them was not as much. It was actually limited. So what does this tell us, really? So basically, this situation really just highlights the importance of genomic surveillance in tracking of AMR, incorporation of genomic surveillance in tracking of AMR, and introduction of highly advanced tools and mechanisms, or AI, in enabling us combat this AMR problem globally. I would like to thank my supervisors, in their absence, Dr. Steven and Dr. Christina. I'd like to thank them for the project. And then my supervisors, Dr. Dawoodi, Dr. Ronald, and Mr. Shahid. They were my supervisors for the project. And also Ms. Becky Chang, in her absence, for helping us with the data. And of course, the ACE AMR working group. Thank you so much.
Thank you so much, Oliver. Yes, Deborah, you can join in.
Hello, everyone. My name is Deborah Neombe, and I am here to share with you about our map web, which is a web-based instance for the rapid microbial analysis pipeline. So we all know these numbers and what they mean. Our AMR is killing people, and it's projected to even kill more people if we don't get a solution soon. But what's even more scary is that this burden is very much on Africa, that for every 100,000 deaths, Africa has the highest number. That's at 23 out of all those. So we really need a solution for this. One of the ways we can tackle AMR is by having accurate knowledge of antibiotic susceptibility. And there are so many phenotypic methods that have been standardized over time to do this. However, these methods have limitations. They require viable bacteria, they have a long turnaround time, and most of all, they drive broad spectrum antibiotic resistance, because as they do them, they have to expose the bacteria to the antibiotics. So we propose the use of genomic methods, which we believe are faster, they have a shorter turnaround time, and they are more sensitive in detecting resistance genes. So I've mentioned about Africa having the highest burden of this issue, and I want to appreciate that recently there's been a lot of funding that is coming in to fund next generation sequencing data generation throughout Africa. However, we still have a gap that we lack scientists that have the bioinformatics skills to analyze this data and get insightful meaning out of it. So the gap here, we realize that there's a lot of data being generated, but then there's little of it that is being interpreted and being used. So we are proposing a solution of RMAP Web, which will simplify data analysis, even for the non-programmers. Before I move forward, I'll tell you about RMAP. So it's a bioinformatics tool that is developed for resistant profiling of escapee pathogens. The escapee pathogens are the global leading pathogens for hospital-acquired infections, and they are all listed on the World Health Organization's list of pathogens that require urgent research and development, hence the interest to develop a pipeline for analyzing these pathogens' resistance. And this pipeline has two versions, version 1 and 2, and you can access them through those links if you have the bioinformatics skills. So now, knowing what RMAP is, what is RMAP Web, it's simply a web-based version of the RMAP tool. I've already told you about the gap between the data generation and the data analysis and interpretation. So the main objective for this work was to empower health professionals and non-programmers to also have a platform where they can do genomic analysis. So that sorry, it's on. Okay, so I was talking about the main objective for this project, and that is to empower people with no programming skills to also do genomic analysis. Okay, so you can access RMAP through this link. If you can do it now, please do, and see how interactive and easy the website is to use. And if you had sequences right now, you'd click the Start Analysis button, and when you do that, it's going to ask you to upload your data. You need a minimum of 3 files. When you upload your data and the upload is completed, you're going to receive an email telling you that your data has been queued, as in waiting in line for analysis. And then when the analysis starts, you get another email that your analysis has started and is running. And then if you're lucky and it completes successfully, you still get another email telling you that your analysis has completed, and you get a link to an HTML file giving you a summary of the statistics of the analysis. And then if you're unlucky and the analysis fails, you still get a notification. And if you have bioinformatics skills, you can go to the log of that and see why your analysis failed. I pulled out a small screenshot of part of the HTML file that you get after your analysis is completed. In this example, I'm showing 3 samples of able money that were analyzed. And here we have that data being compared against 5 different databases. But for this example, we are going to look at only ResFinder. We can see that only 1 sample out of all these has resistance to so many antibiotics. And how is this helpful to a health worker or a clinician? Is that they will know which antibiotics will work for their patient and that will not, and then it will inform their decision on how to move forward. What have we achieved with this? This website was developed throughout last year, and then it was launched in November last year. We had a user training held still in November. And yesterday, Dr. Ida talked about collaboration between different stakeholders. This training had several stakeholders, like people from different fields. We had bioinformatics scientists, students, we had medical doctors, we had resident doctors, we had nurses, and also plant scientists. So I'm glad that actually in that training, we had that collaboration between different people. And as of today, the pipeline has so far run 184 jobs. Looking forward, we hope that RMAP would be expanded to analyze more pathogens, not only the escapee pathogens, because we know that WHO list has more than just the 7 pathogens. So we hope that as we move forward, this will be incorporated so that we can have more genomes and more pathogens analyzed. And I can't leave this podium without talking about some of the limitations we are yet to face. So this was a student-funded scholarship project, and we know what entails in scholarships is that they have timelines and they come to an end. This project, the funding is coming to an end very soon, but would like to continue maintaining this website, and that requires about $1,000 annually. That's the minimum. It could be more depending on how many users we receive. So in case we receive that extra funding, we hope that we'll also expand our computational power to even more cores, because right now we are running at 12, but that gets the users to wait longer, and also because their analysis speeds are slower. So we hope that if we get more computational power, that waiting time will be reduced. I'd like to appreciate the developers of RMAP, Dr. Jared Mboa and Mr. Ivan Serada, because their code was key in developing this website. I also want to appreciate APHRC, who funded this project through the Pauline Bachbinga Memorial Scholarship, and of course Makerere University and ACE for giving us this platform to share with you this work. Thank you.
Thank you so much, Deborah, and sorry about the interruptions. Good enough, you are an African, you understand. You're welcome, Patricia.
Thank you.
Good afternoon, everyone. My name is Patricia, and I'm going to be sharing with you part of my PhD work about antibiotics use and in One Health and temporal alignment between antibiotic introductions and antibiotic-related policies and guidelines in Uganda. So, a short background about this work. Yeah, we all know that every country uses antibiotics, and antibiotics have been introduced at different timelines. And also every country, especially our country, Uganda, has policies that govern the use of these antibiotics. So for this study, I wanted to know how the policies we have align with the antibiotics we have in use especially those antibiotics that are highly used or that have high prevalence of use. And hence this work. And here we are going to talk about policies like the National Action Plan that was talked about yesterday, that was developed in response to antimicrobial resistance. And the purpose of this work is to show to bring out how these policies actually have handled antibiotics use after these antibiotics have been introduced, but at a One Health scale. So One Health is when we look at human, animal, and environmental health interconnectedly. So this is a scoping review and a meta-analysis and a combination of synthesis of policy data. So for the scoping review, it's majorly covering antibiotics use in Uganda. So we looked at studies that have studied antibiotics use, different antibiotics in Uganda. And then I did policy synthesis and also antibiotic introduction synthesis, looking at the timelines of introduction of different antibiotics in relation to policies, as we are going to see. So from the first part of this work that was looking at antibiotics use, wanted to know the prevalence of different antibiotics or the prevalence of use of certain antibiotics classes, and nitromidazoles came out as the antibiotics with that have high prevalence of use. And an example of these are metronidazoles, which are commonly used for common stomach flus, or what we call stomach upsets. And because this antibiotics is used for common infections, it's bound to be used highly, which we expect to have more regulations about their use since they are highly to be used. And some of the antibiotics that are commonly used between animals and humans, that's tetracyclines, TMP, and macrolides. And tetracyclines are highly used in the animal health because they are affordable to buy, but also they are used in animal fattening. So they are mixed in animal feeds to help them increase on their size, but also to prevent infection, especially in poultry. And so from this slide before, when you look at that bar graph, you realize that there is high prevalence of use in humans compared to animals, But when we went further, like to confirm this high prevalence of use in humans, when we did a meta-analysis, we came to realize that actually there is high use in animals compared to humans. And this gave me an idea of, we use drugs, but we use much more drugs in animal production, and we indirectly consume these drugs. So maybe that could contribute to the high prevalence of use in humans, since we feed on animals that are already feeding on a lot of antibiotics. And next, I looked at policy and practice, whereby I'm looking at what's the relationship between the policies that we have in Uganda managing antibiotics use with the antibiotics studies on use in relation to the timeline when these antibiotics were introduced into Uganda or into clinical use. And as you see that we have, I have no point, but the graph in the middle, that's for policies, and below that, those are antibiotics introduction global in blue, and whereas red is for Ugandan antibiotic introductions. And at the top we have the studies that were used in this study to analyze antibiotics use. But when you look at the purple line that shows the timeline for antibiotic introductions, you come to realize that we have a lag between the first policy that was introduced compared to the number of antibiotics that were introduced. So which could have contributed to the rise of antimicrobial resistance, because we took long to start controlling the antibiotics that we're already using into the system. And because of this, we have antimicrobial resistance rising at a high speed, and now it's when we are remembering to introduce policies like the National Action Plan and the Antimicrobial Stewardship Plan, which are coming in years after so many antibiotics have been introduced, but also after resistance has come into play, because we had our first case of resistance back in 1945. So this brought in questions like, why the delay to have these policies come into place? So as Dr. Hope stated yesterday, funding is one of the limited factors. And when you look at the timeline of our policies and the global timelines, our policies have always come after the global policies, because of the global policies, they find the need to fund African countries so that they also put policies into place to control things like antibiotics use, but also antibiotic production. So before we put policies into place, we have to understand the need in our own countries and not wait for international countries to help us actually solve the problems we have at hand. From this study, I came some of the interesting things that I realized that however much we have policies into place, we still have high antibiotics use, and we still have so many drugs being introduced within the market. But we've not looked at the implementation system of these policies. And it same applies to the research that we are doing in antimicrobial resistance. There is so much work that is being done, but this research that is being done has no effect on the day-to-day life of the people that are actually using these drugs or that are actually supplying these drugs, because most of them are not researchers and most of them are not scientists, but they earn from this, so they continue to fund that cause. But how best can we help to solve antimicrobial resistance, not only in doing the research and have it published, but help our governments understand that things like structure matter. Structures start from health centers, one, and also how best can we implement these policies that we've put into place, because Uganda is one of the countries with the best policies, but these policies have not been put into action, and we have no rules and regulations that are enforcing these implementations and also following up how a former policy performed and how best can it be improved. And sometimes we do not actually need to update a policy, but because the policy itself is not the problem, but how this policy is being implemented. And I've already stated the recommendations. So the limitations in this study, there was no publications that had data on antibiotics use in environment. Also, we had no any antibiotic policy regarding environment. So this shows, this actually says a lot, because when we have drugs that are being used in environment right now in animals and humans, but the first policy we released was about human health, and not until 2020 that we had a policy coming out for animal health to control antibiotics use. How long are we going to take to realize that the environment also plays a role in MR in humans, to introduce policies that govern antibiotics use in environment? That's it. Thank you, guys.
Thank you so much.
Thank you.
Thank you so much. Madam Patricia. Yes, Madam Claire, please go ahead.
My name is Rachel Claire Chomkama, as previously introduced. So my work is about discovery of synergistic drug combinations for E. coli, drug information, pathogen response, and disease microenvironment data. Yes, so as all the other speakers have introduced, and today, for the past 2 days, we have been saying AMR is a very big problem Yes, but particularly today, this presentation is going to talk about E. coli, that is amongst the WHO bacterial priority pathogens. So today in Professor Allison's presentation, she talked about development of drugs is actually, besides it being costly and time and taking a lot of time, it only benefits a particular group of people in the population. So that leads to need, or it raises need for us to actually use what is already in existence to enable it to fight our enemy, in this case, which is AMR. So when you look at all the traditional methods that have been fighting AMR in relation to drugs, it looks at developing new drugs or identifying novel compounds or identifying unexplored molecular targets. All this is time consuming. And if we try to take that path, we may not be able to catch up with the enemy. So if we can't go in to develop new drugs or explore novel compounds, meaning we should look out for new solutions. And some of those new solutions are combination therapy, where some of those new solutions is combination therapy, whereby it's a combination of 2 or more drugs in order to treat a certain disease or infection. So that is, if the drugs, when used in combination, the effect is synergistic, then that's when the effect is greater than when used individually. Yes. So that's what we are going to mainly look at. Yeah, so in this study, we developed a machine learning model that can predict whether drug combinations against E. coli are synergistic or antagonistic. So unlike the previous approaches, our methodology integrates multiple factors that influence drug efficacy, such as the drug structure information, pathogen response, and the disease microenvironment data. So, as I said, why machine learning and drug combinations? We have already said developing novel drugs is costly, slow, and complex. But then, as we are trying to develop novel drugs, as we are taking our time, resistance is actually growing. But then, if I'm saying that instead of developing new drugs, let's go out and repurpose what we have. But then when we are repurposing, what method are we looking at? We are looking at drug combination therapy. But then when I talk about remember I said drug combination therapy, that's when drugs, when used in combination, the effect is greater than when used individually. But then as I talk about drug combination therapy, a new problem emerges. We have so many drugs. So if I decided to make combinations, I would have millions and millions of combinations. So if I have millions and millions of combinations and I have to take all these combinations for trials, how much time? I will not have solved anything. So that's where the machine learning comes in. It's going to use all the available data that I'm going to give it, and it is going to narrow down my combinatorial space. So if I had thousands of combinations, maybe it could narrow down to 100 or 50. So instead of taking 1,000 combinations, what if we only take those that are likely to be synergistic? So that's what this pictorial diagram is trying to tell us. Yes, so from the vast combination space where we have millions of drug pairs, we are going to do ML-driven screening based on the data that we have, and then we shall end up with effective synergistic combinations identified. So as I talked about, we have 3 data structures, 3 types of data that we used. We had the drug structure data, the pathogen response data, and the disease microenvironment data. Drug structures that tells us the different substructures that are present in the drug. Then the pathogen response data that tells us, that was measuring the sensitivity of the gene knockout strains of various drugs. Then disease microenvironment data that was telling us how the different metabolites actually affect drug efficacy. So this is our methodology, whereby I start with the 3 data types, whereby we get the drug information data in SMALS format, then we break it down to max keys. Then at the end of the day, I have joint substructure profiles. Then I also get the individual drug genomic data that we later normalize. Then at the end of the day, I also have joint chemogenomic data. So So the reason why at the end of the day we get the joint profiles is because we are looking at combinations. So I analyze the drug structures in pairs because we are looking at combinations of two. So for this particular study, we are looking at quantified synergy was quantified based on the lower additivity model. That is effect based. That means that the effect of the drugs in combination should be greater than the effect of the drug when used individually. Yes, these were the performance of our models. Our main metric was the recall, which was mainly telling us how the model was actually accurately predicting the synergy, how the model was accurately predicting synergy. Yes, these are our drug combinations. So from the from I think 112 drug combinations that we had, only 37 were predicted to be synergistic, which justifies my initial slide that imagine we took all the 112 combinations for trials, how much money would we spend? But now we have narrowed down the combinational space to 37 that are likely to be synergistic. Yes, so from feature importance, we identified those different genes were associated with synergy or antagonism. And when we analyzed our genes, those were the top pathways through which those genes were actually interacting. Yes, so in conclusion, the substructures identified we suspect could be responsible for the binding or stability that enhances the combination effects. And the previous studies that had been done, they either used one of those, they used the data types in silos, but then for us we combined the data set. So the only model that was existing and was better than ours was the cosine model, of which it only used the drug information data. So for them, they left out their model doesn't put into consideration the effects of the media on the drug combination, and also it doesn't factor in the roles genes play when it comes to drug combinations. Yes, so some of the suggestions we have, one of the main challenges is that there was no data. There was limited data while we were trying to do the study. Yeah, so we encourage data sharing and open science practices, and also the study is leading to promising drug combinations that could proceed to validation in clinical and animal studies. Thank you.
Thank you so much, Claire, Rachel, Chomkama. Now, it's time for that kind of discussion. And I love discussions. For those I've taught, they know that it inspires me a lot and it stimulates me a lot. So we are going to have questions from the audience. I have about a couple actually of questions which have been sent to me. Advantages of many people in the audience having my number. They have been forwarding. So I'm going to be rotating from what I have and what others haven't sent. So as I go there, I'll ask each participant using the microphones you have on your desk to just tell us within one line what inspired you to pursue that research question that you pursued. We shall start with Mike. Just within one sentence, what really inspired you to take that direction? Thank you.
Thanks, Shahid, and thanks for the presenters for all that really, really interesting talks. Yeah, that's quite a very hard question, especially as I gave 2 talks. I also want to give, I see Dr. Leonard wants me to say money, but it wasn't money. It wasn't the money. I think it's, I was reading something yesterday from the Nobel Prize winner, the one who got, what? Is it Demis, the one for Google DeepMind, and he was saying how important timing is key for everything when it comes to some of these innovations and problems. And I think one of the key things right now, or the opportunities that we have, is the presence of things like data, but also computing, as Dr. Daudi said earlier. So I think that's, so that was one of the inspirations I think that I had to sort of try and pursue some of these research questions that I'm currently doing, but also their potential. The first one being source attribution, but also the other one being quite very, very well connected to resistance. So yeah, that's
thank you.
That's it. Thank you.
Yeah, thanks. Thanks, Shahid. So on my side, I think the inspiration was drawn from literature review. So the current state of what was happening in the machine learning world in relation to AMR. Most of the work was studying, prediction to a single drug, and yet what's on ground is different. You can be resistant to more than one drug. So I felt it was really a good opportunity to bring in machine learning and see how it can inspire how we look at that direction of multi-drug resistance. Yeah, so I saw a gap and an opportunity.
Basically, I think as well part of it came from literature review, but at first when I looked at what probably, because when I saw the possibilities of what was happening in Cambodia, I sort of felt like it was home. It felt like, yes, it felt like it's what's happening here, because I went and read about the country and the AMR challenges they're having, the policies and everything. It felt home. It felt like the first, so I jumped onto it, but as well, as we were doing the project, then a report comes out, I think in the Lancet under the Graham project, where they were trying to predict future AMR burdens. And one of the regions that had very high AMR burdens that were predicted to be having, I think, high AMR burdens, I think in 2050 or something, it was Southeast Asia, Oceania, and I think Sub-Saharan Africa. But Southeast Asia was topping them. So it intrigued me. I asked myself, what is responsible for this? What is driving this? And I was envisioning that it's possible Uganda can be in the same problem soon. So it really pushed me to go for that research question.
Thank you.
Yes. From my experience using RMAP as a first-year bioinformatics student, if there are any first years here, you know that your first year is really hard. The learning curve is like very sharp, it's like 90 degrees. So my first time using the pipeline was really hard because I didn't know much. But as I advanced in the field of bioinformatics, I got to use it more and find it more efficient. But then that raised the question, the imagination for me, that imagine someone who actually wants to do this, but they don't know any coding or anything. So also working closely with the developers of the original pipeline, I discussed that with them, and yeah, that's how I was inspired to come up with RMAP Web.
Thank you.
So,
yes, Patricia.
What inspired me is when I was talking with my supervisor, trying to develop a concept, I asked him, like, why are we still doing MR? Like, people have done so much work, like, can't all that work, like, provide solutions? And he was like, he asked me and he was like, what do you think is failing? Like, let's go back from the start. And then I'm like, okay, so we start with antibiotics being introduced, and he's like, so what? So from there, like, I was like, okay, so we have policies and antibiotics. And he was like, so what is the relationship between the two? Do you think there is a failure there? Because that's where everything starts. And because most of the research came into play after we have these policies. So he was like, why don't we find out, like, from the back, like using historical data, and we come following up the line and see where did we fail, or where that problem could have started from. So that's why I went back to follow up and see actually, like, where did we sleep on that job? Like, how come we didn't see this coming? And however much we've seen it, why isn't it stopping? And that's why I'm doing something that actually is not scientific, but I felt it's relevant if we are to have our research make meaning. We need to know where the problem came from and where we are failing. Thank you.
Thank you.
So for me, where I draw inspiration from is that, so during my internship with Dr. Ronald, when I just joined DS, he gives us very many papers to read. I'm from a computer science background, and then I'm like, oh my goodness, these things are so many. But as you read and then we get to understand what AMR is, I get interested in, we realize that there are very many models that have been built, kind of similar to what I've done. But the difference is that they were using the data in silos. So given my computer science background, I'm like, if we give the model, if we give the model all this data, or if we combine this data set to get one and incorporate all these factors, can we get a better model that can predict better effective synergistic combinations? Yes, that's my inspiration.
Oh, wow. Thank you so much. I asked that question because you are a career scientist, so I know you are getting a lot of inspiration from many places. So I wanted us to learn from that. Yes, our first question from here.
Thank you very much. My first question goes to Mr. Mutegeki, and then maybe also the other panelists. So besides UTI and malaria, what other conditions would be of higher priority when it comes to AMR prevention and management in women, pregnant mothers, and neonates for Uganda and then globally? Then the second question, I think, goes to the doctors in the house, and then also the panelists. Can a lifetime medical record of inclusive can a lifetime medical record of inclusive a lifetime medical record inclusive of every OTC drug patient interaction guide a prescribing doctor on real-time AMR prevention prescription in real time, specific for every individual patient?
Okay. Mr. Mutegeki, the first question.
Yeah, thanks. Thanks. Very interesting question, and yeah, I'll give a very direct answer. From my point of view, I would say sepsis as another very key disease that highly affects women in the MR area.
Thank you so much. Any doctor to tackle the second question? It was for the audience. Yes. You want her to repeat the question? Oh, did you mean physicians or doctors are many? Yes? Did you mean clinicians to direct the question to? Was it for clinicians in the room or? Yes. Yes. Please elaborate.
Okay. So let me first repeat the question. Can a lifetime medical record inclusive of every OTC drug patient interaction guide a prescribing doctor or nurse or clinician on a real-time AMR preventive prescription? Because what normally happens right now, we first wait for a patient to first develop signs and symptoms of AMR resistance, and maybe that's when doctors or the nurses can come in to change the drug that is being administered. So, so the question goes, if we are to come up with a solution, it would be helpful for the doctors, the nurses, and maybe the clinicians. But the question is open, but I think a doctor would be more appropriate to answer. I don't know.
The question is open, so me, I'm going to dictate something. Yes, you have an answer? Okay. Yes, Dr. Gariwang wants to try it out. As the audience ponders, I will not forget. Before we leave here, someone has to come up with a solution also.
Yes. Yeah, thank you. That's a good question. Actually, the optimistic answer is yes, if you wanted a brief one. But the other complicated answer is that it's near real time, not real time. So it's going to be complicated to be real time because there's some element of a small lag. So there's some work that we are currently actually doing, in the Daring project that is actually looking at clinical data without incorporating AST results and other data that delays the process to actually do exactly that. And we've discussed various models that we can develop, including, for example, prediction of UTIs, sepsis, so that when you're at the clinic, you can actually input the data that you have from the patient, and then you get a prediction. Yes.
Thank you so much. That's why he's a doctor, right? Yes, he's giving the solutions. Thank you so much, Dr. Ronald. I have a question here for Patricia. From a One Health perspective, how important is cross-sector collaboration between human health, veterinary, and environmental sectors in addressing antimicrobial resistance? As you answer that, I'll look for another. Yes.
So, as I had already discussed, back in 2010, when we started highly noticing the issue of antimicrobial resistance, this was in human health. And spanning from that time to 2020, most of the research covered human health, until when a few research started in environment and the animal sector, and people are like, oh, we've implemented public interventions like washing hands, improving people's sanitation, but why do we still have antimicrobial resistance, or why do we still see so many pathogens developing resistance? Until when they started doing similar research in the animal health and veterinary health, and they found that there is also resistance because these other parts of One Health, the animals and the environment, cannot complain, cannot speak up. So they couldn't inform us that, oh, we also have the resistance. So until when we noticed and we are like, why don't we try to find out whether these other organs also have resistance? And when we found resistance, that's when they started urging research to look at the relationship between the resistance in animals and humans. What is the relationship between the two? But if we had done this from the start, we could have avoided the much damage that we have at hand right now. But because we decided to look at one domain at hand, and this is why we have antimicrobial resistance pitching up as high as it is right now.
Thank you so much. Let's have one more question.
All right, thank you. So my question is to Patricia. Thank you for letting us know that as much as the breakthrough of antibiotics was, the success was short-lived. But my question is that who bears responsibility for delayed policy? If you recall, it won't be until 2001 before WHO released the global strategy on containment of antimicrobial resistance. So who bears the responsibility for this delayed policy? And also, do you think innovation can actually spur, speedy policy? Let's use AI, for instance. The breakthrough of AI brought about, AI strategy, AI ethics, AI governance, and the likes. So do you think, innovations can also spur, speedy policy? Thank you.
Thank you for those questions. So for the first one, who bears the consequences of the delay? Of course, it's us humans. I wouldn't say that people who use drugs, because we all do use these drugs, but the biggest problem is funding, and also it's because independent ministries of health for different countries wait for the collective voice, like WHO, like UN, to talk about a problem to be actually an issue. Before, I'll give an example of COVID. Before the WHO came out to say that COVID-19 was had become a pandemic, most countries didn't care. They thought it was a problem only for China. So before like such big organizations come out to alert us about something, we often ignore our own. So meaning in our individual countries, we haven't done enough to know the actual problems that we are facing. And that's why when we run onto the bandwagon of like, there is a policy for this, I release the policy, but I've not laid groundwork for this policy that it's going to be implemented onto. So we have rules and regulations in place, but they have no structure that is upholding these policies. And so it's still us who will suffer at the end of the day. And hope I've answered your first question. And for the second one, please, I beg your pardon for the second question.
So do you think innovation can spur speedy policies?
So I don't think innovation can delay policy. I feel like it necessitates or enables policies, but still, however much we have, I'll ask a question like, how many of the antibiotics that we use in Africa are actually manufactured in Africa? And then we have done research, which is good, like on drug combinations or dosage lowering of antibiotics that are being phased out. And we actually show evidence that they are working. But this research is not helping us because we are not doing the manufacture of these antibiotics. We have not put in funding into our pharmaceutical production or into the actual clinical research of trying out these drugs and say, oh, at the African Center of Excellence, a student found out that these drugs can work hand in hand. Our government should come into play and be like, support this work and help to actually idealize this information. We've not done that. So we have so many technologies that are coming up and researchers are embarking on these technologies, and policymakers will go on to make policy and say, oh, actually AI can help us with MR, but that stops on paper. It actually doesn't go into implementation, and which means we are not solving the problem. We are actually talking about it, but we are not doing the actual solving. So I feel like technology is playing its key, but we haven't done the bare minimum work that needs to be done. I know most of us in this room cannot do that work, but I know people like Dr. Hope, who are actually in contact with Ministry of Health, can persuade the Ministry of Health to actually help build the groundwork so that we see that the work we are doing today as researchers is actually helping our own people. Thank you.
Thank you so much, Patricia. I have a question here for Mike. Your findings show that multi-drug resistance lineages across a global spread. How should genomic surveillance systems adapt to monitor these different transmission dynamics? That is for Mike.
Thanks, Shahid, for the question. Whoever has asked the question. So I think, yeah, it was I think interesting to hear. It was sort of interesting to hear Patricia's discussion just previously, because in my mind I was also thinking we don't really need, because the thing with AMR, it's also very, very multi-dimensional. Like, it's not a single, let's get the drugs out there and then this is done. So there are quite some other initiatives, like even something I wouldn't call it simple, but things like surveillance and, like what people in this room are doing, being able to track, being able to track the presence of these elements in our environments. I think this is all very, very useful work that also is able to do something. And I mean, obviously, the question of how policy leaders should take that up on is always very complicated because the way they work is very, very, very different. But back to the question of with the more drug resistance, I think surveillance should start to also, and maybe it is already doing that, sort of target sort of complex lineages, and then also see how these can be reported. See how this can be reported within our ministries. Like in the UK, one of the examples that I like to tell, even in the same city radius of like 1 hour, it's possible to go to a hospital and be treated using different antibiotics because of the knowledge sharing of the surveillance, So it's not that, if you go to this, if you've got this sort of issue, it's always going to be amoxicillin because it's in a massive book of guidelines. But actually, they are always sort of revolving and tracking the presence. So they won't recommend you the drug if they have identified that in the area where you are living, they are seeing high levels of resistance, because then they know they're just going to increase it. So even something like that is, I don't know if we do that here already, obviously, but that's sort of ways of how actually real-time surveillance is being sort of used. Yeah.
Thank you so much. Next question is here.
Thank you all. Claire, I have a question for you. Based on your experience in drug combinational therapies, I believe you're more or less an expert. Are there successful clinical trials from drug combinations developed using AI?
Are there successful drug combinations which have been predicted by AI, right? Yes.
I can't give you the exact drug combination, but I think you should look out for a paper that is called The Caramel, that went beyond predicting the drug combinations and actually tried, I think, predicting the dosages of the drugs. I think they went a further step into seeing the trials of proceeding to the trials.
Okay.
Have I answered your question?
Is it answered? She's saying meaning nothing yet, or like in that paper, is there something or there is nothing yet?
There is something.
All right. Thank you so much. She's going to read the paper. Yeah. Yes. The second last question will go to Oliver. Many resistance genes were associated with the plasmids and the transposons, according to what you said. How significant is horizontal gene transfer compared to clonal spread in driving antimicrobial resistance in these pathogens in just less than a minute?
All right. In terms of significance, these two mechanisms are mainly complementary to each other. I cannot tell you that maybe this drives it more or this drives it more, that clonal expansion is better or horizontal gene transfer is the main driver, but they are complementary mechanisms in that the strain harbors the plasmid, which maintains the resistance. It's more like the strain is about who's expanding, and then the mobile genetic element or the plasmid is more about what resistance is being spread. But what's still about the mobile genetic elements, for them, as I explained before, apart from they are spreading horizontally, which is really fast, but also they can spread resistance across species. like they can spread. You can find an MR gene spread from E. coli and then taken to maybe Salmonella, which can really be dangerous. Thank you.
All right. Hi. I had two comments to Henry. The first one, you started your presentation by looking at the process of the clinician interacting with the patient and the number of days, the lag in between. Could you describe that same process with the machine learning model? What's different in terms of the output? And then the other is maybe a comment to Patricia on the context that you were speaking about for the policies. Perhaps if you could look at the budgetary allocation to health over the time that you are looking into to see if there's a policy, and you have already hinted on it that possibly it's an issue of funding. Could the budget allocation have changed after the policy came through, or it was exactly the same and that is why you're not seeing any change? The other is the source of information on what you called use of antimicrobials. Are you looking at the instance of an antibiotic being used, meaning it's something out of 100%, or would you be interested in the volume of the antibiotics that either distributed, utilized, such and such that your data source would be let's say the WHO GLASS platforms that look at how much is imported, both human and, GLASS is for human, and then the World Organization for Animal Health for animal. You may find some differences in your conclusions, given that a larger volume of antibiotics are actually used in animals than in human. Purely based on the population difference. There are more animals than humans. But you may find some differences, although the entire idea and your research is quite impressive on looking at the impact of policy on the volume of antibiotics being used. Just a twitch in the data sources, and then adding a little bit of context on what you call structures, using the budget allocation to health as a proxy indicator for structures, or even human resource. I think that's data that is readily available. In terms of health, the proportion of, the ratio of a clinician to patient kind of thing. Thank you.
Thank you so much for that comment. Henry?
Yeah, thanks, Dr. Vivian. So maybe just to recap what the machine learning, the traditional pipeline, or what's on ground. From hour 0, the patient comes and then a sample is taken, and then, from hour 1 to 48, the culture is done, and then by hour 72, which is the third day, we get the results of whether they are susceptible or resistant. So what machine learning tries to do is, over time, we've curated this data from these tests, so it's not generating any new data. We're using historical data that has been curated from such kinds of processes, and we're saying that, can we reduce the time it takes by leveraging, how machine learning works, which is to get large sums of data and understand the patterns that connect people with different characteristics. So for example, if we're looking at patient medical history, let's say maybe someone has had surgeries before, meaning the likelihood of exposure to antibiotics in the past has been maybe higher, or they've been on ICU departments for long, that could also be a potential exposure. So it looks at the patient medical history, in that in this case, from hour 0, when the patient arrives, we're not taking off a sample. In this case, we are taking off, we are sort of triaging the patient to take off vital information, which will now become very key to feed into a system that has been created, whose backbone is the machine learning model that has been trained on this vast amount of data, meaning examples of patients in the past who have had certain characteristics and their result was susceptible or resistant, and then learned the patterns in that data, and now can tell us with a new example, this patient who has come, based on their demographics and other history data, can they tell us to which category this patient will lie? So it sort of reduces this turnaround time from the 3 days to literally about seconds, let's say 30 seconds, depending on the volume of data being entered. But also, this is not to say that this is the final output. So it's just giving the clinician a range of possible antibiotics that from which they could prescribe based on the profile of susceptibility and resistance, so that the clinician can make informed decisions when attending to this patient, but also inform other things. Can we do an extra test based on this patient's profile, or if they want to find out any other thing that could potentially give them a go-ahead to make the final decision. So it's, these kinds of systems are called human in the loop, where the doctor is the human, but they're assistive tools to make the pipeline more efficient. And through this, a doctor can be able to see as many patients in the shortest period of time, but also make personalized treatment decisions based on the patient's history. Yeah, thanks.
Thank you so much, Henry, for the comment. I have here a comment or a question. Actually, there are many, but there is one which is intriguing. I'm just going to mention the comment. It's not a question. Shahid, is it possible for Deborah to be invited to the MSc Bioinformatics class to give us an elaborative approach on how she turned a command line tool into a web-based tool? That is the comment. It's more of a question, but a comment. So to me, I will say on behalf of the department, I can create that time, but I cannot answer for her. So let me just give her 1 second to just either say yes or no. Yes, it's a comment, but it has a question tag at the end. Is it possible so?
Yes.
Yes. So whoever sent the question, yes, it can be arranged and it will be arranged. Thank you so much, everyone. Thanks so much for the panelists. Please give them a hand of applause. Yes, and also the audience, you were quite engaging. Thank you so much, and that's the end of this session. Back to the MC. Thank you.
Please don't go. Please, Mike.
I think there is a picture.
There is a picture
Is it
here.
a picture
Yeah,
or a photo?
please, both.
Okay.
Please take a picture with.
Yes, we can just.
Could you help us?
Yeah.
Yeah. So thank you very much for participating in all the sessions today. So this is how we are going to move going forward. We have just 3 items to go. One is the award ceremony for. One is the award ceremony for the best posters and best presentations, I think. After that, we shall have closing remarks. And after closing remarks, we will have a closing photo. And after that, the 4th item is a tea and networking session right downstairs. Thank you very much, our panelists, for the evening. At this juncture, I would like to invite Namuswe and Gloria to come and assist with the award-giving ceremony. And I'm privileged to invite Dr. Galiwango to come and give out the awards to the winners. Thank you.
Hello, everyone. Hi. So we've come to the most exciting part of the symposium, the award ceremony. Let's all clap for ourselves for reaching here. Okay. So for these 2 days, we've had wonderful oral and poster presentations. And also, let's clap for our oral and poster presenters. Wonderful job, guys. The judges definitely had a difficult job. I'm glad it wasn't mine. For this reason, we are going to award 2 poster presenters and 1 oral presenter. First off, second place poster presentation award goes to John Paul Okeke. Please come forward. And the first place poster presentation award goes to Christine Nantongo. Definitely a very beautiful poster. And the best representation award goes to Justice Ohene Amofa.
So I've been told you can present those certificates in the bank and get a loan.
Wonderful job, everyone. Oh, we're glad to have you at the ACE.
Yes, another round of applause for the winners. Finally, we've come to the end of our symposium, and I would like to say that I'm honored to invite Dr. Daudi Jingo to come and give us the closing remarks. After the closing remarks, please stay around. We are going to have some photographs here. Thank you. Please welcome Dr. Jing.
Yes, these such symposiums have a knack of ending just when they're beginning to be enjoyable, don't they? After such a rich menu and a rich array of presentations, you know, I wish we had another 2 or 3 days, because I could almost sense people getting into their own, you know. And moreover, by the way, whether you know it or not, this is the first multinational AI for AMR symposium or conference on the continent. So, if we had certificates, everybody would be given a certificate, because, like Dr. Galwango said, you would show it everywhere. It's bankable, as it were. And by the way, it is both a joke but not a joke also, because as we all know, really, AI is only just beginning in terms of how much it can do. If it was a 10-chapter book, we are still in the first half of chapter 1 in terms of what AI could do. And we know it is evolving really fast. So you are right in the driving seat. Like our executive director likes saying, it's a great time to be a young person starting off in science, because you have tools that nobody has ever had before, and so a great opportunity to make a huge difference. Anyway, we want to thank everybody for the contribution that they have made to this, the amazing talks, the unbelievable panels, the great posters, the great talks. You know, I looked at some of those posters, and again, we're always constrained by time. I think we need a full day on those posters. We walk one by one on everybody's poster, and they tell us what's going on, because each of them has great science. But also, you guys are from all over the place, you know, from all the 10 countries. Did we say 10 countries? 10 countries. So we are very privileged to host you. Please keep coming back. Some of you have been here before on related conferences. Please keep your eyes out. More will be coming. But most importantly, we're looking forward to great science from you guys throughout your careers, because you're all just beginning. So that is something that, and when we see something, AI and AMR or AI and anything, and it's somebody who attended this conference, it will be one of our happiest moments, because we'll know, okay, at least they got some idea from that conference, or they got some motivation, or they met somebody who they are working with, or they got challenged by something, and that means that we'll be self-replicating in that manner. So, I think we all deserve a round of applause for ourselves, and we wish you all the best journeys back to wherever you're going. There are some people who are going 1 mile away from here, and others who are going hundreds and hundreds of kilometers, but we hope you will all reach fine, and great to see you, and see you again very soon. Thank you.
Well. Thank you very much, Dr. Jing, and thank you, everybody. Can we come for a group photo at the front? And then I've been informed that there are souvenirs for everybody down at the basement. So as you go for your tea, please do not forget to pick your souvenir. Everybody is a winner. So,